Welcome to the new video. So today in this lecture we are going to discuss a very important topic, vector space. This is the heart of linear algebra. Students, this lecture is especially designed for semester exams. Okay, so let us begin the journey. At first we will see an overview that what we are going to discuss in this lecture. So at first we will see the introduction of vector space, then we will see the application that in which fields these are going to be used. Okay, then we will see the definition of vector space. After that we will solve lot of questions related on vector space only. Okay, there will be about 18 to 20 questions, okay, which is related to vector space only. Okay, and I have picked the question from very standard books like Friedberg. Okay, this is very famous and well renowned book. Okay, and I have taken the question from the very famous book XK Mappa. Okay, this is an Indian author, and another author Dr. A.P. Singh. Okay, and after that we will see the summary of this lecture, and then we will see the references, and by this we will end the lecture. Okay, so this will be my content of this video. So next, so introduction, right? See, I have written a brief introduction about vector space. Just go through it. Okay, I have written it in a very simple language, right? Just go through it. Next, now we will see the application of vector space, right? See, these are the applications in the core areas. In the core areas, this is used in the field of computer graphics and animations, in the field of data science and machine learning, and in the study of physics and engineering. Okay, see, here is transformation, scaling, rotation, translation, right? These things, this you will learn in the upcoming lectures. Okay, just go through it, right? And in the broader fields, it is used in the field of signal and image processing, economics and optimization, and beyond the basic you can see that this will be used to read the functional analysis in finite dimensional spaces and tensor analysis also. Okay, so there are lot of application of this, but here I have written few just to show you the importance of this topic. Okay, next, now we will see the definition of vector space, right? See, so this is the definition of vector space, and if you read from here to here line by line, you will be get confused and you don't remember anything. Okay, and your reaction will be like, oh, how can I remember that? Okay, for that I am going to teach you in a very simple way so that you can remember for a long time if you are reading this first time. Okay, especially this video is designed for the new learners. Okay, so see, I hope you have the basic idea of set theory. Okay, see, now the question arises that what is a vector space, right? So vector space is nothing but just a set. What kind of set? So a set is called a vector space if it satisfies some certain conditions, right? So basically vector space is a set, and that set is called a vector space when it satisfies some condition. Now we will see that what are those conditions, right? See, a non-empty set. Okay, if a non-empty set is closed, just remember my words, right? Just listen my words carefully so that only you can remember it. See, a non-empty set after being closed under addition and scalar multiplication. Okay, suppose there is a non-empty set and it is closed under addition and scalar multiplication. After that, till here this is the first step, that a non-empty set is closed under addition and scalar multiplication. After that, if it satisfies all these four properties under addition, okay, a non-empty set is, now at first a non-empty set is closed under addition and scalar multiplication, then under addition it satisfies these four conditions. After that, under scalar multiplication it will satisfy these four conditions. Okay, only then we will say that this non-empty set is a vector space. Okay, so how will you remember it? That if a non-empty set is closed under addition and scalar multiplication, after that if it will satisfy the commutativity, associativity, identity and inverse under addition, and these four properties under scalar multiplication, then we will say that this non-empty set is a vector space. Okay, so this is the definition. Okay, I have just given you the overview that how will you remember through this structure. Okay, now we will discuss that what is closure property, right? What is commutativity, associativity, identity inverse, and what are these things? A, B, X, Y, what are these things and from where it is coming? This is very important thing. Okay, so see, now what is closure property? See, I am introducing the terms step by step so that you can understand and remember it easily. Okay, so let's see what is closure property. Suppose you have a set A, right? And you are taking two elements from that set, right? After that you are operating operation in between them. After operating an operation between those two elements, you will get a new element, right? And now if this new element is still a member of that set, then we will say that this set is closed under this binary operation. Okay, basically what are you doing? You are taking a set. Okay, now from that set you are taking two elements. Okay, between those two elements you are operating an operation, right? And after operating between those two elements you are getting a new element. Now see, if this member is still a member of that set, then you will say that this set is closed under this binary operation. Okay, see, what is the operations? Basically here we will see operations plus, minus means addition, subtraction, multiplication and division, right? I think you don't understand anything. Okay, so don't worry, I am giving you the example so that you will be able to understand easily, right? See, I am giving you some examples. Okay, see, we are taking a set of natural numbers. Okay, now we will see that under addition, does it is closed, right? So suppose if you take any two elements from here, take any two, suppose you are taking 2 and 3, and you are operating with plus, what will you get? You will get 5. Okay, and this 5 is still the member of that set. Okay, take any two elements, okay, and operate with plus, and you will get that still the result is the member of this set, right? So set of natural number is closed under addition, right? Set of natural number is closed under addition. Okay, now what about subtraction? See, if you take any two elements from this set, suppose you are taking 1, right, and another element taking 5, right, and now you are operating with minus, what will be the result? It will be minus 4. But see, minus 4 is not a member of this natural number set, right? So what is the conclusion? It means that set of natural number is not closed under subtraction, right? What about multiplication? If you take any two elements, suppose you are taking 4 and 5, okay, and you are operating with multiplication, what will be the result? It will be 20, and this is still the member of this set, right? Hence, what is the conclusion? The conclusion is that the set of natural number is closed under multiplication, right? Now we will see about division. Suppose you are taking two elements 5 and 4, okay, 5 and 4. Now take the operation division, right? What will be the result? Whatever the result is, but it will not belongs to the natural number, right? So the set of natural number is not closed under division, right? Do you understand now? Yes. Now we will see about the set of integer. In this case you can see that the set of integer is closed under addition. No doubt, if you take any two elements, suppose 2 and 3, you are operating with plus, you will get 5, and still this is the member of that set, right? And it will follow for all the elements of Z, right? Now what about subtraction? Take any two elements, 3, 5, operate with minus, you will get -2, and -2 is still the member of this set, right? Set of integers. Hence, what is the conclusion? That the set of integers is closed under addition, the set of integers is closed under subtraction, right? Similarly, if you take any two integers, suppose you are taking -2 into 3 or any other integers, and you are multiplying with multiplying between them, you will get a result which will be the element of that set, right? And it will follow for all, right? So what is the conclusion? That the set of integers is closed under multiplication. But what about division? Again, if you take 1 and 2, you operate, right? This will not belongs to the set of integers, right? What is this? This is basically 1 divided by 2. This is another notation, right? This is not from the set of integers. Hence, the set of integers is not closed under division, right? Now, what about the set of rational numbers? Okay, see, under addition, if you take any two rational number, okay, suppose you are taking 3/2 plus 5/2, okay, whatever the result is, okay, what is the result? 8/2, and you can see that this is again the member of rational number, right? So it will follow for all the numbers, right? So set of rational number is closed under addition. Similarly, it will be closed under subtraction, and it will be closed under multiplication, and it will be closed under division also. But there is a catch. What is the catch? See, when does it follow? It will follow only when, suppose a by b is a rational number, right? It will only follow when the denominator is not equal to 0. Right. So what is the conclusion? That set of rational number is closed under division only when the denominator is not equal to 0. Right. When the denominator is not equal to 0. Right. This is the condition. Just remember it. That the set of rational number is closed under division only when the denominator is not equal to 0. Right. So see, what is remaining? Now it is set of real number. What about this? See, so undoubtedly you can see that set of real number is closed under addition, set of real number is closed under subtraction also, and it will be closed under multiplication and closed under division also. And here again the denominator will be equal to 0. Okay, now I am giving you a question to think, right? See, what about the set of irrational numbers, right? Take a equal to set of irrational number. Now just think, is it closed under addition? Is it closed under subtraction? Is it closed under multiplication? Is it closed under division? Right? So this is your homework, right? You can comment the answer, right? I will make you reply. Okay? So this is your task, right? So this is the basic introduction of closure property, right? Or these are the examples so that you can understand it easily, right? So we will move to the next term. Now we will discuss about field and vectors, right? For that, let us move to the definition what I have given to you. See, now I will read the definition again, right? But now this time you have to understand each and every word. What does it mean? Right. So see, at first let us give it a name. Suppose this is the set V. Right. Suppose this is the set V and it has two elements x and y, which is arbitrary. Right. And what I have said that a non-empty set is closed under addition and scalar multiplication. This was the step 1. right? What does it mean? That if B is closed under addition, what does it mean? That if you take any two elements x and y, okay, and you add them, then you will get the result, and that result will belong to B, right? This is the meaning of closure. Okay, and what is the meaning of scalar multiplication? Right, see, here is a catch. Here I have talked about the multiplication, only multiplication, right? And here I am talking about scalar multiplication. Remember, these two are different things, right? How? Let us give a brief introduction, right? See, so here is the brief introduction to multiplication and scalar multiplication. Basically I am showing you the difference between them, right? What about multiplication? Suppose there is a set V, okay, you are taking any two elements from that set and you are operating multiplication in between them, right? Basically you are doing multiplication on the elements from the same set, right? This is multiplication, okay? And when you are applying multiplication on two elements, one from a set V and another from another set F, okay, basically this F is a field, right? And the elements of the fields are called scalars, right? What I have said, that this is a set V, right? You are taking an element from here and this is a field, okay, and we are denoting with F. Now the question may arises in your mind that what is field, right? So you don't need to worry about that. Just remember that in the case of scalar multiplication, one element is coming from the set V and another element will come from a field, right? What is field we will discuss later, okay? And taking an element from V and taking an element from the field F, you will multiply and you will get a result, okay? So this operation is called scalar multiplication. Why the word scalar? Because the elements of field are called scalars, right? The elements of field are called scalars, right? That's why the name is scalar multiplication, right? You may take here two elements, right? Suppose there is another element B, right? And you can operate like that, a into x plus y, right? And a plus b into x, okay? So this is the basic difference, right? And here we are talking about scalar multiplication, not only this multiplication, right? So see, the more you are getting in the subject, it becoming more complicated, right? So that's why at first I have given you the basic structure. After that I am explaining each and everything so that you can understand and remember things easily, right? So see, yes, what does it mean that a non-empty set V is closed under addition? Means this, and it is closed under scalar multiplication. What does it mean? That if you take any two elements, one element from V, one element from field F, okay, and if you multiply them, okay, you will get a result and this result will belongs to V. This means that this V is closed under this scalar multiplication. I think I am able to make it clear to you, right? Okay, see, as non-empty set V is closed under addition and scalar multiplication, right? What does it mean? It means this and this, right? After that it will satisfy commutativity. Now the question arises that what is commutativity? So I am writing here, commutativity means if you take any two elements from the set V, okay, then it will satisfy this condition, right? X plus y equal to y plus x, where x and y are belonging from the set V, right? And what does it mean by associativity? If you take three elements, right, plus z, it will be equal to x plus y plus z, where x, y, z are from V, right? And what about identity? There will be an element 0, okay, such that it will be equal to 0 plus x, it will be equal to x, right, where 0 is belonging from the set V, right? This is identity. In the case of addition, 0 is the identity element, right? This will play a very crucial role in future throughout this lecture, okay? Very good. And what about the inverse? If there is an element x in V, okay, then there will be another element y, such that when you operate with addition, you will get the identity element 0, right? Then this element is called inverse, right? Or for better writing, you can write like that: x plus y, x plus y equal to y plus x equal to 0, right? Under scalar multiplication, it will satisfy these four conditions. Now I will show you that which element is belonging from where. Okay, let us see it. So in the first case, 1 into x equal to x, okay, for all x belongs to V, and where 1 is belonging from the field, okay, see, here it is scalar multiplication. What does it mean? It means that one element will be from the field, right? So in this case here, 1 is from the field and x is from the set V, right? And it will satisfy for all x. Similarly, if you take two elements AB from V, right, AB from AB from field, okay, and we denote the field by F, right, and x from V, right, then this property will satisfy. Similarly, here A is belonging from F and x and y is belonging from V, okay, after that this condition will satisfy, okay. Similarly, here also A and B is belonging from F and x is belonging from V, right? So now I am giving you the notation. This was the backstory of vector space, right? So how does we denote a vector space? See, we will denote a vector space by V over F, right, where F is a field, okay. For a scalar multiplication, the elements will come from this side, okay, and this is the non-empty set what I have given here, and this is the non-empty set, okay. And one thing, that the elements of field is called scalars, okay, and the elements of the set V is called vectors, okay. This is the notation. What does it mean? That V is a vector space over the field F. Wait, I am writing here, right, in the next page. Now let us talk about the notations briefly, okay. See, we denote the vector space by V first bracket F, okay, and we read it like V is a vector space over the field F. What is field? Do not worry about that. I will teach you in future when it is needed the most, okay. And the elements of the V are called vectors and the elements of the field F are called scalar, okay. So these are the basic notations, right? Now again, let's see the definition. What does it mean? That let V is a non-empty set and it is closed under addition and scalar multiplication. After being closed, it satisfies this condition and these conditions, okay. Then this set is called a vector space. By this discussion, now we are ready to read the definition of vector space, right? So let's read it. See what it is saying. A vector space or linear space. This is another name, okay. A vector space V over a field F consists of a set on which two binary operations called addition and scalar multiplication respectively are defined so that for each pair of elements x, y in V, there is a unique element x plus y in V. What it is saying? See, it is saying that V over a field F consists a set on which two operations. What does it mean? V over a field F consists two binary operations, addition and scalar multiplication. Okay, are defined so that for each pair of elements x, y in V, there is a unique element x plus y in V. What does it mean? For all x, y in V, there is a unique element x plus y in V. What does it mean? It means that V is closed under addition, right? V is closed under addition, right? And secondly, for each element A in F, for each element A in F means A is from the field, right? And for each x in V, and for each x in V, there is a unique element AX in V. What does it mean? That V is closed under scalar multiplication, right? After that, the following condition holds. What are the conditions? Under addition, commutativity, associativity, this is identity and this is inverse. All four satisfies. Under scalar multiplication, see this, all are satisfied. Okay, then this set is called a vector space over a field F. Okay, and here the elements x plus y are called sum of x and y, and ax are called the product of a and x. Okay, so this was the basic introduction of vector space, and this is the way to read and visualize the definition, right? So we will move to the problems now. Okay, we will solve a lot of problems in this lecture. Okay, so next, so let's move to our first question. Okay, see, this is our first question. Actually, this is a theorem. We have to prove it. I know that in the case of pure mathematics, you will be so much frustrated that you are not able to prove the theorem, or you are not able to understand the proof, or you are not able to remember the theorem's proof, right? But in this lecture, I will show that how to prove the theorem, and or how can we approach to prove the theorem, so that it will be very easy and interesting for you in the further journey. Okay, see what it is saying. It is saying that in a vector space V over a field F, okay, these all four conditions hold, right? So we will prove all of these. Okay, see, here is a catch. Here it is not written, but I am writing for you. Here this 0 is belonging from the field. Okay, this 0 is belonging from field, right? And this is a vector. What kind of vector? Null vector, or you can say that this is a 0 vector, right? This is 0 vector and it belongs to the set V, right? And the elements of F is called scalar, so 0 is a scalar, and the elements of V is called a vector. So this is a 0 scalar and this is null vector or 0 vector, right? And I will use this notation instead of it, right? I will use this notation because you are familiar with it, right? So let us prove it. So see, what is the correct way to prove a theorem? So at first write whatever is given in the statement. Okay, after that we will think that what we have to do, right? So see, what is given? It is given that in a vector space V over a field F, okay, only this much is given, right? So what is given? That V is a vector space over a field F. Okay, so write it. It is given that V is a vector space over a field F, right? So from here, what can we say? We can say that V is closed under addition, right? This is from the definition of vector space. And V is closed under scalar multiplication. Then under addition, V will satisfy the commutativity, associativity, then identity, right? Then inverse, right? And under scalar multiplication, it will satisfy four conditions, right? 2, 3, and the last condition was a plus v into x equal to ax plus bx, right? So this is given to us, right? Using these things only, we have to prove that this condition, this condition, this condition and this condition holds, right? So let's prove it. Now you have to know something about field, right? Means some properties about field. So just remember that in a field F, right, in a field F there will be always an identity element. This is obvious. Means if any set is a field, then it is obvious that there will be an identity element. Means without identity element there will be no field, right? And the second one is that for each element there will be an inverse element, right? And see, here are especially two types of inverse elements. One is additive inverse element, right? And second is multiplicative inverse element, right? And this multiplicative inverse element exists only for non-zero elements, right? So basically you have to remember only two things. What? That in a field 0 is always belonging from there, and the second one is that inverse of each element belonging from that field, right? So using these and these things only we will prove all of these, right? So see, we will prove by using the identity element of the field, right? So see, we know that we know that 0 belongs to F, right? And 0 plus 0 will always be equal to 0, right? And these all are from the field. Okay, now we will operate alpha from right side in both sides. Okay, so see, since we are working in a vector space V, so it will satisfy all the properties, right? Let me write some name, that V, this is vector space property 1, right? This is vector space property 2, this is vector space property 3, this is vector space property 4, this is 5, 6, 7, right? And this is vector space property 8, right? So see, since we are working in a vector space, so by using this property, what will we get? See, what is here? This is A is from field, B is from field, right? And X is from V, right? And this satisfies this condition. Similarly, we can say that from VS8 we get that this is A, this is B. So 0 into alpha, what it will be? It will be 0 alpha, right? 0 alpha. Here A is 0 and X is alpha, right? Plus B alpha, right? So this will be 0 into alpha equal to 0 alpha. Okay, by using VS8, right? Now see, I am talking about something very interesting thing. See, what is here? 0 is belonging from F, right? And alpha is belonging from V, right? So 0 into alpha, what it is? This is actually scalar multiplication, right? And we know that scalar multiplication, that V is closed under scalar multiplication. It implies that 0 and alpha will be belonging from the set V, right? This we get from the definition of vector space, right? And after that, just notice one thing, that in V there is inverse element for each element. Means since 0 alpha belongs to V, right, and this is a member of a vector space V, so the additive inverse will also exist, right? It means that 0 into alpha will also belongs to V, right? Why? Because this is the additive inverse, right? Now we will add this element from both sides here, right? So add it. It implies minus 0 alpha plus 0 alpha plus 0 alpha equal to minus 0 alpha plus 0 alpha, right? We just adding this 0 alpha, right, from both sides. Now we will use associative property, right? Because associative property is satisfied here, right? So it will be minus 0 alpha plus 0 alpha plus 0 alpha equal to minus 0 alpha plus 0 alpha, right? Which implies that from where we get is from VS2, right, from associative property. Now see, this is the element of V, this is the element of V, right, and this is an element and this is the inverse of it, right? So from here what will we get? That what was the property? That if X is any element and if you add with any inverse element, then you will get identity element of that vector space V, and this identity element will belong from V, right? And each element of V is nothing but just a vector, right? So this is the identity element. Clear? Very good. So this is an element of V, this is an element of V, means this is a vector, this is a vector, right? So what it will be? It will be 0 vector. Why? Because these are additive inverse, right? Plus 0 alpha equal to, similarly these are also additive inverse, so this will be 0 vector, right? From where we get, we are getting it from VS4, right? VS4, right? Now see, from the identity element what we get, that x plus 0 means 0 vector plus 0 vector plus x, it will be equal to x, right? So from VS3 what we get, that 0 vector plus 0 alpha, it will be equal to 0 alpha, right, which will be equal to 0 vector, right, from VS3, and this is proved, right? So number 1 is proved. Now the question arises that what is the significance of it, means what is the beauty? See, what we have done, that you are taking any 0 scalar, right, and you are multiplying with any vector, right, and what you are getting? You are getting a null vector, right? So this is the result. Okay, so what is the geometry behind it? Let's see it. So see, this is our vector of length alpha, and we are multiplying with 0 scalar and we get this 0 vector. Now let's prove the second one, right? What it is saying, that C into 0 vector equal to 0 vector for all C belongs to F, means C is belonging from the field, means C is an scalar, right? So next page. See what we have to prove. We have to prove that C into 0 vector is always a 0 vector, right, and C belongs to F. So how can we prove it, right? So we know that, see, in this case what we have done, we have taken the element from field, right? Now we will take the element from V, right? So we know that this 0 vector belongs to V, right? This is actually 0 vector, right? I am just mixing up the notation, sorry for that, right? This will be 0 vector, this is 0 and this will be 0 vector. Just manage it, okay? So we know that null vector belongs to V, and we know that null vector plus null vector equal to null vector, right? See, what is the difference? In this case, this was from field, right? This was a scalar, means 0 scalar plus 0 scalar equal to 0 scalar, right? Then we proceed like that. But in this case, this is vector, right? Just know the differences, only then you can enjoy the beauty of mathematics, right? Now we will operate the scalar C from both sides, right? C into this equal to C into this, right, where C belongs to F. Okay, now what does it imply? See, what was the seventh property? This was actually that A into x plus y is equal to ax plus ay, right? This was our VS7. So we will use this condition here, right? This is my scalar and these are my vectors, right? So this is my scalar, these are my vectors. So what will be it? It will be ax plus ay, means c0 plus c0, right? So just write it, c into 0 vector plus c into 0 vector equal to c into 0 vector, right? Now it implies, see, one thing again, we know that C belongs to F, right, and 0 vector belongs to V, and after, if you do the scalar multiplication C into 0 vector, it will also belongs to V. Why? Because V is closed under scalar multiplication. Since this is a member of V, it implies that inverse of this element will also be there, means the additive on inverse of C into 0 vector will also belongs to V, right? Now we will operate it from, now we will add this both side, right? So add it, see, C into 0, C into this, right, plus minus of this equal to C this plus minus of C over this, right? Which implies, now we will use the associative property, right? So use it. It will be C this plus minus C of this is equal to what it will be? It will be C0 plus minus of C of this, right? All of these are vectors, right? So now from where we get it from VS2, right? VS2 na? Yes, by associative property. Now what is this? This is additive inverse. So what will we get? We will get 0 vector, right? So write it, C into 0 vector plus what it will be 0 vector equal to what it will be? It will be 0 vector. From where? From VS4, right? See, these are very simple things. We just need to remember the logic or understand the logic, right? And from the identity property, what will we get? We will get that this equal to this, right? This is from VS3, right? Yeah, hence proved. Right? So what will be the geometry of it? See, this is your 2D plane, right? And this is your 0 vector, this is your null vector, right? And if you multiply with any scalar, right, if you multiply this vector with any scalar, it may be any scalar, okay, then still the result will be like this, okay, this vector. So this is the geometry of it, right? So we have completed 2 proofs, right? Now you may be confused, or in future you may be forget that how to prove it when you learn more and more, right? So for that I am just giving you some memorizing tip, that when you prove tips, what tips? You have proved 2 results, right? That 0 into alpha is equal to 0 vector and C into 0 vector is equal to 0 vector, right? Just remember, when you prove this, right, just go through this element, right, from field, okay? Just use this condition, and when you prove this, just use this thing to prove it, right? I know you may think that this is very simple, I can remember it, but believe me, when you study higher, it will forget, right? That's why I am saying that whenever you trying to prove it in future, just go through this, and when you try to prove this, just go through this, right? So next, what it is saying, that 1 alpha equal to alpha. Sorry, there is a mistake. Let me correct it. Right. So what it is saying, that we have to prove that minus 1 into alpha equal to minus alpha for all alpha belongs to V, and where 1 is the identity element of the field F. Right. So let's prove it. What we have to prove, that number 3. 1 second. It was number 3 minus 1 into alpha equal to minus alpha. We have to prove it, right? Where 1 is the element of field and alpha is the element of V. Right. See, one thing more. What I have said about the field, that if this is a field, then it must have a 0 element, right? It must have inverse of each element, right? And 1 is there also, that it must have a unity element, means 1, right? Just remember that in a field, 0 and 1 is always there, and inverse of each element under addition and scalar multiplication will always be there, where scalar multiplication will, where the inverse of scalar multiplication will exist only for non-zero elements, right? Okay, see, we have to prove it. So let us prove. We know, we will use this now, right? We know 1 belongs to F, right? So since 1 belongs to F, and we know that in field inverse of each element is there, right? What does it mean? That the additive inverse of 1 will also be there, right? And it will be equal to 0, right? Because this is the property of inverse, that if you have any element and if you add it with its additive inverse, then you will get 0 element in field also, right? So now we will operate alpha both side, right? See, actually this is element of field, this is element of field, and this 0 is element of field, means this 0 is an scalar, right? And these are also scalars. Okay, see, I am teaching each and everything by very simple way and explaining it in that way so that you can understand, right? So see, 1 plus minus 1 operating with alpha, you will get 0 alpha, right? Which implies, now we will use this condition. Which condition? VS8, right? VS8 na? Yes, VS8. So what will we get? We will get that 1 alpha plus minus of 1 alpha is equal to 0 alpha from VS8, right? Which implies, and we know that 1 into alpha, what does it mean? See, there was a condition, right? What was the condition? That 1 into x will always be equal to x, right? And this was my VS6, right? So by using the VS6, what will we get here? We will get that 1 into alpha will be equal to alpha, right? Plus minus 1 into alpha equal to 0 alpha from VS6 na, from VS6, right? VS6, yes. Now see, we will use the same logic here again. Okay, since alpha belongs to V, right, and V is a vector space, so its additive inverse minus alpha will also be belongs to V, right? Now we will add this minus alpha from both sides. Okay, so add it, minus alpha plus alpha, right, plus minus 1 into alpha, right, equal to minus alpha plus 0 alpha, right? It implies, now we will use the associative law, right? So use it. Minus alpha plus alpha, right, plus minus 1 into alpha equal to minus alpha plus 0 alpha, right? It implies, from where we get it from associative law, and it was Vs2, right? And from inverse, what will we get? We will get it a 0 vector, right? 0 vector plus minus 1 into alpha is equal to, see, at first let me write it, Vs inverse property, it was Vs4, right? So write it from Vs4, right? Now see the right hand side, what it is? It is minus alpha plus 0 alpha, right? And what it is? Recently we have proved that 0 alpha is equal to 0 vector, right? We have proved it, na? See, we have proved it. This is our first one, right? 0 into alpha equal to 0 vector. By using that thing, what will we get? We will get here 0 alpha equal to 0 vector, right? Which implies we get it from first one, right? Now which implies 0 vector plus any vector, where does it will belong? It will belong from V, and it will be equal to minus 1 into alpha equal to, what it will be? It will be minus alpha, right? This is from Vs3 identity, right? This is from identity Vs3, right? This is from Vs3. Okay, so our result is proved. Okay, so this was the proof of this result, right? So see the overview. At first we took 1 belongs to F, then we use the additive inverse property, right? Then we operate alpha from right side, right? Then we use the Vs8 property, then we use Vs6 property here, right? After that we add minus alpha both side, right? Then we use associative law, right? Then we use inverse property, right? We get this vector, and in RHS this was our proven result, which we had proved earlier. We use this, okay? Then we use identity property, right? So we get this result, and hence this is proved, right? See, this is an element of field, right? And this is an element of vector, so their scalar multiplication will be an element of V, right? So this was the proof, right? Proved. So next one, now we will prove this. Okay, what it is saying? It is saying that if C alpha is equal to 0 vector, then either C will be equal to 0 or alpha will be equal to 0 vector, right? See what it is saying, that if you are multiplying a scalar and a vector, and if you are getting a 0 vector, then either scalar will be 0 or vector will be 0, right? So we will prove in two part, right? Case 1, case 2. At first we will let that if C is not equal to 0, then alpha will be 0, right? And in the second case we will prove that if alpha is not equal to 0, then C will be equal to 0, right? By this we will end the proof, right? So let case 1. Suppose if C is not equal to 0, right? And since C is from the field, so if C is not equal to 0, then C inverse will be from the field, right? And now we have that C alpha equal to 0 vector. This we have, right? Just there is a difference of notation, right? I think you are habituated with that, right? So see, we have this, right? C alpha equal to 0 vector, and we know that inverse of C exists, so we are operating inverse from both sides, right? We get this, right? After that we use the associative property under scalar multiplication, what was given in the definition, right? This property, right? We get this, right? Then we use this property 1 into x equal to x, which was the first property of scalar multiplication, right? 1 into alpha, right? C inverse C, it is equal to 1, right? into alpha, right? We get this, and after using this condition we get this 1 into alpha equal to alpha, we get this, then we get alpha equal to 0 vector, right? So see what we assume, we assume that if c is not equal to 0, then alpha is equal to 0, right? So if this condition holds and c is not equal to 0, then we prove that alpha will be equal to 0, right? So let's move to the case 2, that suppose alpha is not equal to 0 vector, right? Then we have to show that c is equal to 0. So what we have done, that this condition hold, if this is not equal to 0, then this is equal to 0. Now we are proving that if this is not equal to 0, then this will be equal to 0, right? So how can we prove? We will prove it by contradiction, right? So we will assume that c is not equal to 0, right? We will prove it by contradiction, right? So if possible, let c is not equal to 0, and since c is not equal to 0, so inverse will be there, right? And similarly we have this condition, right? And we will proceed it in a similar way, right? See, right, we have proceeded in a similar way, and we get alpha equal to 0 vector, which is a contradiction. Why? Because we let that alpha is not equal to 0, right? And hence our assumption is wrong, and if alpha is not equal to 0, then c will be equal to 0, right? This is similar, just go through it, you will understand it easily, right? So see, therefore we have proved that if c alpha is equal to 0 vector, then either c equal to 0 or alpha equal to 0 vector. This is proved, right? So actually see, there is a catch. Do you know about the contradiction? If you are a beginner, then you may be confused. So I am saying that what is contradiction? Contradiction just relate like that. Suppose you are going to your friend's house, right? This is your road, right? You are going to your friend's house, then you have seen that the road has divided into two parts here, right? One is gone to this side and another is gone to this side, and you are the first time visitor to your friend's house, right? So you stand here, that after coming from this side you stand here, right? And you are seeing that there are only two paths, this way and this way, right? And you don't know that which is correct one, so you assume that this path is my correct, okay? And then you followed, and then when you followed, you go there, and you see that the road has become to an end and there is no way there, right? So what you get? You get that you come here, right? And you get two options from this side or this side, right? And you choose this side by thinking that this side is my correct, and you find that this side is not correct, right? This was wrong way. So what does it mean? What is the conclusion? The conclusion is that the right path was this one, right? So this is the concept of contradiction, that you are this is the concept of contradiction, that you are thinking that this path will be correct, right? And you are going through this and you are getting some problem, right? And then you are failing the assumption, right? And you are getting that the opposite was correct, right? So this was the short idea of contradiction, right? We used this one here, right? So next one. So what it is saying? It is saying that in any vector space V, so that this condition holds, right? See, you can think that this is a very simple simplification, right? Yes, it is, but there is a beauty behind it, right? What is that? I will show you. So see, what is given? It is given that V is a vector space over V, right? So what we have? We have this thing, that V is a vector space, right? And these conditions hold, right? So let us begin. It is saying that a plus b into x plus y. We have these things, okay. Then it will be equal to, we will use this property, right? So it will be a into x plus y, right? We are using this property, right? We are taking this as a single vector, right? We are treating it as a single vector, right? Means a, what was there, a plus b into x equal to ax plus bx, right? Similarly, a plus b into a into this vector plus b into this vector, right? From where we get it from VS8, right? From this property, okay. Then what it will be, then we will use this property, right? It will be ax plus ay plus bx plus by from VS8, right? And hence proved, right? So this was the proof. We are using only these two conditions, right? Similarly, you can prove it in another way. How? You can take this as a single scalar, right? You can treat it as a single scalar, then you will use this property, right? So this is homework for you. Prove this by using this result, right? So now you can say that this is a very simplification and we know that, but what is the beauty behind it? What is the beauty behind it? So the beauty is in the graph, right? In the geometry of it, right? So see, we know the vector addition, right? So we know that if this is a vector x, right, which has a direction and length, right, and this is a vector y, right? So if we add these two vectors, then this will be my addition of that two vectors x plus y, right? Now if you multiply this vector with a scalar a, right, then this will stretch where a and b are positive. Just remember that I have taken it a and b to be positive here, right? So this was my x, right, and this will be my ax, and this was my x, and this is my bx, right? And when you add, you will get ax plus bx, okay. Very good. And similarly, this was my y, and you multiply with a, you get this, right? And you multiply with b, you get this, right? You get this. Then ay plus by was, then ay plus by will be this vector from here to here, right? Now use tip-tail method, put this vector here, right? Put this vector here, then you will get something like that. Then add this, right? Then what it will be? It will be this vector plus this vector. This vector was ax plus bx, right? Ax plus bx, and this vector was ay plus by, right? So this is my, this vector plus this vector means this vector is equal to ax plus ay bx plus by, right? And the equation is saying, means this is saying that this vector is equal to this vector. What does it mean? It means that if you multiply this vector with a plus b directly, what? If you multiply this vector with a plus b directly, then you will get this same vector. See, I have written here. You multiplied this xy vector with a plus b directly, right, and you get this. And here you can see that this vector and these vectors are same, right? So this is the geometry of it, okay. See, this was my analytical part, right, and this was my geometrical part. I hope you understand it. If not, then please review it again, okay. So next, so listen, till now whatever we have proved was just a theorem and result, right? So from now we are going to solve the problems. And what will be the approach? Basically you have given a set, right, and you have to prove that this set is a vector space or not, right? So how to prove it in your semester exam? right? Now I am going to teach you that, right? So see what is given that so that the set of all elements of the form this where ABC belongs to rational number form a vector space over the field Q under usual addition and scalar multiplication of real numbers, right? So see, here it is given that this is a set, right? Okay, this is the set, okay, and the field is considered as Q, right? Means the scalars will comes from the rational number. Okay, so listen, how can we prove it? So at first we will construct the set with these elements, right? So write it. See, let V equal to this set. Okay, now we have to show that this set is a vector space. For that, what we have to show? We have to show that this is V, and we have to show that this V is closed under addition, this V is closed under scalar multiplication. After that, we will show that this V satisfies these four properties under addition and these four properties under scalar multiplication, right? So at first we will prove that V is closed under addition, right? So let's do it. Closure under addition, right? See, what is the procedure to show the closure? At first we will take any two elements from the set, right? Then we will show that the addition of those two elements is still belonging to the set V, right? So at first we have chosen two elements x and y from V. Now the question arises that how does this x and y looks like, right? So this x and y will looks like this, right? In this form, right? So we have taken this like x equal to a₁, b₁, c₁, right? In this form, and y equal to a₂ plus b√2 plus c₂ plus 3√3, right? We have taken two elements. Now we will add them, right? X plus y, and where a₁, a₂, b₁, b2, c₁, c2 belongs to the field of rational number, right? It is given in the question. Then we have added this x plus y, where x is equal to this one, plus y is equal to this one, right? So we can separate it, and we can take this here to here, right? Here to here and here to here, and after taking common we get this, right? Why? Because we are working in set of rational number, and commutativity is allowed in the set of rational numbers, right? And after that, what we see, there is a catch. X plus y, we get this, right? And see, a₁ and a₂ both are rational numbers, and we have proved recently that set of rational number is closed under addition, right? What does it mean? It means that a₁ plus a₂ will belongs to rational number, b₁ plus b2 will belongs to the rational number, and c₁ plus c2 will belong to the rational number, right? See, since we know that a₁, a₂ belongs to Q, it implies a₁ plus a₂ belongs to Q. In a similar way, we can show that b₁ plus b2 and c₁ plus c2 belongs to Q. What does it mean? It means that x plus y belongs to V. How? See, I am showing you, right? Since this is a rational number, right? This is a rational number, this is a rational number, right? Suppose let it be d1, right, plus this is d2 root 2 plus d3 3 root 3, right? See, this is in the form of this, right? That's why this belongs to this. I have just changed the name here, right? Instead of a, I have taken d1, instead of b, I have taken d2, instead of c, I have taken d3, right? And where d1, d2, d3 are from set of rational numbers, right? So that's why we can say that x plus y means this expression is belonging from the set V, right? And since x plus y belongs to V, it implies that V is closed under addition, right? Clear? Okay. So next, now we will show that this set is closed under scalar multiplication. After that, we will show these properties and these properties, right? So see, closure under scalar multiplication. Okay. So what will we take? We will take an element from the field, right, and we will take another element from V, right? So see, we have taken an element lambda from Q and another element x from V, right? See, in the definition I have used a, b, right, as scalars and x as vectors, but here I am taking lambda as a scalar. I am just changing the notation, right, so that you can habituate with it, easily, right? And in future it will be helpful for you, right? So just read it. So let lambda belongs to the field q and x belongs to the set v, right? Now we will take the scalar multiplication of it. Then lambda into x, what it will be? Lambda will be as it is and x will be of the form this, right? So see, lambda into let x equal to this one, right? I have not written that x equal to this one, but you can write where x equal to this and abc belongs to q, right? Then we can multiply it because we have already proved the results, right? So see, after multiplying you get this, right? And see here, a is from set of rational number, lambda is from set of rational number, so their product will also be from set of rational number, because earlier we have proved that set of rational number is closed under multiplication. Similarly, lambda into b and lambda into c will be from set of rational number, right? So see, right, these are from set of rational numbers. Since these are from set of rational numbers, then this is of the form this one, right? You can take lambda into a some other thing, e plus this one f root 2 plus g root 3, right? You can take it, but I am leaving it here. I hope you understand it. It implies that lambda into x belongs to b, and therefore b is closed under scalar multiplication also, right? So what we have done, we have taken the set, then we have showed that a is closed under, b is closed under addition and scalar multiplication, right? Now step by step we will show that this will satisfy commutativity, associativity, identity and inverse, right? After that we will show all of these. So let's begin. So see, VS1 vector space property 1 commutativity. Okay, what will we take? We will take any two elements from that set V, right? And then we will show that x plus y equal to y plus x, right? See, we have taken two elements, x equal to this, y equal to this, which is belonging from the set V, right? Then what will be x plus y? X plus y will be this, right, as we have done before. And after we rearrange it, we will get this one, right? And now we will find the y plus x, right? So let's do it. X plus y equal to this and y plus x equal to this, y plus x, right? Y is this one, x is this one, right? We are adding this, and by rearranging we will get this, right? a2 plus a1, this, right? And see, since these are from the set of rational numbers and we know that set of rational numbers are commutative, right? So we can write it like a2 plus a1, we can write it a1 plus a2, b2 plus b1, we can write it b1 plus b2, and c2 plus c1, we can write it c1 plus c2, right? So see, x plus y was this, y plus x was this, right? And see, these are both equal, right? So we can say that therefore x plus y equal to y plus x, and therefore commutativity satisfied, right? Now next we will show associativity. Vector space property 2, associativity, right? So what will we do? We take any three elements from the set V, right? Then we add the first one and then the last one, right? And after that we will add the last one, then the first one, right? And after then we will see that the result will be same. See, at first we have taken three elements x, y, z from the set V, and it will be of the form this, right? And see, now x plus y plus z, right, means x plus y. At first we will add this, and after that this addition we will add this, right? So after adding this we will get this, right, plus this one, right? Now when you add this one, you will get that a1 plus a2 plus a3 will be one side, then b1 plus b2 plus b3 root 2 another side, and then c1 plus c2 plus c3 into 3 root 3 another side, right? Just separate it. Okay, you will get this. Now we will check this one, x plus y plus z, which will be equal to, this is x plus y plus z, this is y, this is z. Clear? Now when you add this, you will get this one, right? a2 plus a3, b2 plus b3, c2 plus c3, right? After that you will get this when you add this with this one. So see, x plus y then plus z, this was this, and x plus y plus z was this, right? And see, these both are equals, means associativity satisfied, right? So we have proved that commutativity, we have proved that closed under addition satisfied, closed under scalar multiplication is satisfied, closed under commutativity satisfied, sorry, commutativity satisfied, associativity satisfied. Now under addition, two properties are remaining, those are inverse and identity. So let's prove it in the next page. Identity, how can we prove it? We know that identity means x plus 0 equal to x, right? Or 0 plus x equal to x, right? So see, at first we will take an element x from set V, right? And we will take another element 0 from the set V. At first we have to check that does this 0 belongs to that set V or not, right? So for that we have to do this. See, since our structure was like that, see, a plus b root 2 plus c 3 root 3, where abc belongs to c, right? See, here abc is belonging from c, so we can take a and b and c is equal to 0, because 0 is an irrational number. So we are taking a special case that a and b and c are equal to 0. Since a, b and c are equal to 0, so this will be 0 plus 0 root 2 plus 0 root 3, right, which will be equal to 0, right? So we are doing this one, right, to take the identity, right? So see, this belongs to V undoubtedly, right? So next, take an element from set V, x, any arbitrary element, right, this one. Then we will check that x plus 0 and 0 plus x belongs equal to x or not. See, x plus 0, we are adding it, this one plus this one, right? Then we will get a plus 0 plus b plus 0 plus b plus 0 root 2 plus c plus 0 3 root 3, right? And after adding this, we will get a plus b root 2 plus c 3 root 3, which is equal to x, right? What does it mean? And similarly we can get that x plus 0 equal to x, and similarly we can get that 0 plus x will always be equal to x. Sorry, this is not 0, this is x, right? This will be my x, right? Just make a correction here. After that, you can see it like that, and therefore identity exists, right? So we have proved that identity exists. Now we will talk about the associativity. See, sorry, we will talk about the inverse. Let x belongs to this, and now remember my words, since see, since a, b, c belongs to q, and we know that additive inverse of each element in q exists in q, right? What does it mean? It means that if any element alpha belongs to q, then minus alpha will also belongs from that set q, right? This is a result, okay? So by using this, we will get that minus a, minus b and minus c will belongs to this set, right? By using these scalars, right, we will form a vector, this one, right? Since minus a, minus b, minus c belongs to q, so minus a plus minus b root 2 plus minus c 3 root 3 will belongs to v, right? Undoubtedly. Now take it, now give this a name, a new name. We are giving it a new name, minus x, right? Now we are adding it, x plus minus x, x plus minus x, we will get this, right? Now add it. When you add it, you will get like this, and we know that minus a minus a, b minus b and c minus c is equal to 0, right? So we get this. So we are adding we have an element and we are adding another element and we are getting identity. What does it mean? It means that this one is inverse, and similarly we will get it for minus x plus x, right? So see, okay, let me do it first. This is equal to x, not 0, okay? This is equal to x, right? So similarly we can write this one, that so similarly we can show that minus x plus x equal to 0, hence inverse exists. So see, till now we have proved that B is closed under addition and scalar multiplication. Then we have showed that B satisfies commutativity, associativity, identity and inverse. Now we will show these 4 results one by one, right? So let's begin. At first we will prove this one, that 1 into x equal to x, right? This is my vector space property 5, right? So let x equal to this one belonging from the set V, right? Then 1 into x, it will be equal to this, right? Then after multiplying we will get this one, and we know that 1 into a is always a, 1 into b is always b, and 1 into c is always c, right? So this one and this one is equal to x, hence 1 into x equal to x holds, right? See, this one is belonging from set of field, right? This one is from field, means rational number, right? This is not from V, okay, by definition. So next we will prove this one, where alpha and beta will be from the field and x will be from the V, right? Earlier we have used a b, but we are using here alpha beta. Why? Because we are using this a and b here, right? So see, let x equal to this one belongs to V and alpha beta belongs to Q from the field, right? Next, let alpha beta into x, it will be equal to alpha beta into x, means this one, right? Now we will multiply it. After multiplying we will get this one, alpha beta into a, alpha beta into b this one, alpha beta into c this one, right? Now we will use the associative property, means it holds in. Now why? Because it holds in Q. See, alpha beta, those are belonging from field, and a, this is also belonging from the field, right? And we know that in the field of rational number this property holds. You can associate, right? So we are changing the bracket, okay? Alpha into b alpha, alpha into b beta root 2, right? And alpha into b c 3 root 3, right? Now see, we are taking alpha as a common. After taking common we will get this ba, this one, this one, this one, right? Now from this side we will take beta as a common, right? So take it, alpha was my outside and you are taking beta common, you will get this, and we know that this one is equal to x, right? This one is equal to x, hence alpha into beta x, right? This is alpha, this is beta, and this one is x. So what we get? We get that alpha into beta x equal to alpha into beta x, and this holds, right? So we have showed that these two holds. Now we have to prove the remaining these two, right? So next, now we will prove the next one. See, vector space property 7, right? What it is? It is alpha into x plus y equal to alpha x plus alpha y, right? So how will we start? At first we will take two elements x and y from V and one element alpha from the field, right? Then we will start from here, right? And after simplification and solving we will get this, right? So this will be our approach. So let us begin. At first let x and y belongs to V, where x will be look like this and y will be looks like this, okay? And alpha belongs to Q, right? Field, okay? Now take LHS. What it is? It is alpha into x plus y, means alpha into this is my x plus this is my y, right? Now after solving this we will get this expression, right? a1 plus a2 plus b1 plus b2 root 2 plus c1 plus c2 3 root 3, right? Now we will multiply this, okay? So multiply with each term separately, we will get this, right? Now again we will multiply it, right? After doing that, we will get alpha a1 alpha a2 plus alpha b1 root 2 plus alpha b2 root 2 plus alpha c1, this one. Okay, now we will rearrange it. How? At first we will take this term plus this term plus this term, right? So see, at first we have taken this term plus this term, right? Now we will take alpha common, right? So take it, we have taken alpha common from both of it, right? Now see, this is my x, right? What it is? It is my x and this is my y, right? So it will be alpha x plus alpha y. So you can see that we have taken LHS and we get RHS, right? This one. So from here we can say that alpha of x plus y equal to alpha x plus alpha y holds, right? So we have showed that all the properties hold, right? Now we have to show one remaining property, right? That is VS8. Okay, so let's prove that. Now we will prove the last one, right? Vector space property 8, right? What it is? It is alpha plus beta into x equal to alpha x plus beta x, where alpha and beta are belonging from the field and x is belonging from the set V, right? So see, let x equal to this one, right, where ABC belongs to Q, as you know, then alpha beta belongs to Q, right? Now we will start from LHS, right? So let LHS, this one is my LHS, right, equal to, we will put the expression of x, right? Now we will multiply it individually, alpha plus beta a, alpha plus beta into this, alpha plus beta into this, right? So do it. After multiplying, you will get this one, right? Now multiply this a with these things. Okay, it will be alpha a plus beta a and this one, right? After doing this, just rearrange it. At first we are taking this term plus this term plus this term, right? And then we will take this term plus this term plus this term, right? Do it. After taking this, you will get this, right? Now take alpha common from it, right? You took alpha common from it and beta from here, right? What you get? You get this expression. And see, this is my x and this is my x. Now put it, right? So what we get? Alpha x plus beta x. So see, alpha plus beta x equal to alpha x plus beta x. We have proved, right? So therefore alpha plus beta x equal to alpha x plus beta x holds, right? So see what we have done. We have taken a set V, right? After that we have showed that it is closed under addition and scalar multiplication. After that we have proved that it satisfies commutativity, associativity, identity and inverse, and we proved that this satisfies all the four conditions of it, right? So what can we say? That V is a vector space over the field Q, right? So right, since V satisfies all the conditions from VS1 to VS8, hence we can conclude that V is a vector space over the field Q, right? And how can we denote it? It will be denoted like V over Q, right, where V is my vector space and Q is my field, right? So this was my proof, right? And if in the semester exam it will be given, then you have to prove like that. Only then you will get full marks. Okay, there is no chance to cut any single marks, right? So next one, see. So see what it is saying. It is saying that so that the set of all real convergent sequences is a vector space over the field of real numbers, right? See, basically here are two new terms, that set of all real convergent sequence, right? So we have to take a set that we have to take a set B equal to set of all convergent sequences, right? Then we have to show that B is closed under addition, B is closed under scalar multiplication, and under addition it will satisfy these four conditions, and under scalar multiplication this will satisfy these conditions, right? So at first we have to know that what is sequence, right? Then we have to know that what is convergent sequence, right? See, basically this is the part of real analysis. You will read it in real analysis in a very deep way, right? Basically there is a separate chapter about that, right? But here we don't need that much, right? If you are a beginner and you don't know anything about it, right, then I will give you some idea so that you will be able to prove this, right? So I am not going to teach this in depth here, right, but I am going to give you a brief idea, right? So see, at first we will learn that what is sequence. So see, this is the mathematical definition of sequence, right, and this is the idea. You can read it. I am just going to explain it through the examples, right, so that you will be able to understand that what is going on. See, this is basically a sequence xn equal to n, and where n is belonging from the natural number, right, and if you put, then it will be 1 2 3 4 5 6 and so on, right? And what about it? This will be 1 by n, and if you put, then it will be 1 1 by 2 1 by 3 1 by 4 1 by 5 and so on, right? And what about it? It will be, if n is equal to 0, sorry, if n is equal to 1, then it will be minus 1. N can't be 0. Why? Because n is a natural number, right, and natural number starts from 1, not from 0, right? So if n is equal to 2, it will be 1. If n is equal to 3, it will be minus 1. If n is equal to 4, it will be 1. If n is equal to 5, it will be minus 1 and so on, right? So see, these are the sequences. These are called the sequences. There are a lot of sequences in many varieties, but I have taken just these three so that I will be able to make you understand easily, right? So see, this is a sequence. Now tell me, does this sequence converge to anyone? Does this sequence converge to anywhere? No, because after 6 it will be 7, then 8, then 9, then 10, and then so on, so on, so on, dot, 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 dot. It will be go to infinity, right? And what about that? See, I am going to take it like this way. This is my 0, this is my 1, right? And what will be 1 by 2? 1 by 2 will be here. 1 by 3 will be somewhere like here. 1 by 4 will be here, right? 1 by 5 here, 6 here, 7 here, 8 here, 9 here, and this. Okay. And see, 1 by 1000, it will be like here. 1 by 2000, it will be here, right? The more you take n, the more it will get closer to 0, right? So see, and see, it will never cross the value 0, right? So 0 is the last one where it can be converged, right? If you take n equal to infinity, n tends to infinity, then it will be 1 by infinity equal to 0, right? These are actually concept of limit, right? But don't worry about that, just to see the idea, right? So see, this is actually going towards 0, not exactly 0, but this is going to 0, going towards 0. Remember my word, going towards 0, right? And what about it? This is actually not going to anywhere. This is actually oscillating from 1 and minus 1, right? So we have seen three type of sequences. One is going to infinity, another is going to 0, and another is going to 1 and minus 1, right? So when does we say that a sequence is convergent? So we say that a sequence xn is convergent only when this will converge towards a real number L, right, and where L belongs to real number. It will converge to L and where L belongs to real number, and it should be unique, right. Only then we will say that the sequence is convergent, right. If so, see, in this case xn equal to n, this is going to infinity, it means this is not convergent, it is divergent, right. And when, and in this case, see, the sequence is going to a unique number, unique real number, right. That's why this sequence is convergent, right. And in this case, see, this sequence is not going to any unique real number. Sometimes it goes to 1, sometimes it goes to -1. That's why this is not convergent, right. There is a special name for it. It is oscillatory sequence, right. So we get the conclusion that if a sequence tends to infinity or minus infinity, it will be divergent. If a sequence is tends to a real number, and if that real number is unique, then we say that the sequence is convergent, right. And if a sequence converges to more than one real number, then we say that this sequence is not convergent, it is oscillatory sequence, right. So I hope I am able to make you understand the concept, right. Just remember, see, this is another type of sequence, right. If let it be xn, right, then what it will be, it will, if n goes to infinity, then it will goes to 0, right, and this sequence will go to converge to 2, and 2 belongs to real number, right, and this is unique, that's why this sequence is convergent, right. But this is not convergent. Why? Because it is alternating between -1 and 1, right. So see some important facts, that if limit is unique, then it is convergent. If xn tends to infinity or minus infinity, this is divergent. And if it goes to two real numbers, two different real numbers, then the sequence is called oscillatory, right. And here is the summary of it, that a sequence is convergent if xn tends to L, where L is a real number, right. Remember it, where L is a real number. And a constant sequence, right, this is always convergent, this is always convergent. Remember my word, constant sequence are always convergent, right. Like if you take 1 1 1 1 1 1 1 dot 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 dot, it will be always convergent and it will converge to 1, right. If you take 5 5 5 5 5, it will always convergent and it will converge to 5, right. Similarly, if you take any xn equal to c, right, it will always converge to c, where c is a constant, right. And if a sequence tends to infinity, then it is divergent, and minus infinity, it is also divergent. This is the example, n tends to infinity, n tends to minus infinity, right. Oscillatory, there is no limit, right, no unique limit, right, and bounded but not convergent. See, this is an example that the sequence is bounded but not convergent. Why? Because we know that sine always behaves like that, like that. Now, that's why this is oscillatory. This is not tending to a unique limit, right. Sometimes it is +1, sometimes it is -1. This is oscillatory, right, and it is bounded but not convergent. So what is the conclusion? A sequence may converge, diverge to infinity or oscillate, right. So the problem for what we are doing this is all about convergent sequence, right. Just remember that. Next, now we are seeing the algebra of convergent sequence, right. We will use it to prove that. Okay, so listen it carefully. Suppose there is a sequence xn that is convergence to L, another sequence yn that is convergence to M, right. Now the question arises, then the sum of those sequence, where does it converge? It will converge to L plus M, right. and xn minus yn converges to L minus m. A into xn will converge to AL, right, where A is an scalar. Okay, do you understand? I think you will be able to understand, right? And constant term, it will always converge to that point. Okay, and xn yn it will converge to L into m, means xn yn it will converge to Lm, right? And xn by yn it will converge L by m, where m is not equal to 0, right? And if xn converges to L, then minus xn will converge to minus L, right? And it will hold for absolute value also, this one, right? So all operations are term-wise and limit behave like real numbers, right? So this was the brief idea of sequences. I hope you understand it. See, basically I am explaining just for you, so that you will understand, even though you are the beginner of this subject, right? And even you don't know anything about real analysis, right? So let's prove it. Now let us consider a set V. So see, this is my V, right, where V equal to xn and xn is my convergent sequence, right? So what will we do? At first we will show that V is closed under addition and scalar multiplication. After that we will show these four conditions and these four conditions, right? So let us prove the closure under addition first, right? So let's choose any two elements xy from V, right? Let xy belongings to V, right? Then how does this x and y looks like? Then x will be equal to xn, right? Means x is basically a sequence, a convergent sequence, right? And y will be like this. Okay, now see what we have done. We have taken a set, right? Then we took two elements from there, where x will be a convergent sequence xn and y will be a convergent sequence yn, right? Now see, since xn is convergent, what does it mean? It will converge to a real number which will be unique, right? Similarly, since y is a convergent sequence, it means that it will also converge to a real number that will be unique, right? So let us suppose that xn is converging to L and yn is converging to m, right? From here we are getting it from the definition of convergent sequence, right? So see, xn converges to L and yn converges to m, right? And since xn converges to L, what does it mean? That L is a real number and it is unique. Similarly, m is a real number and it is unique, right? This we are getting by the convergence definition, right? This one, right? I am writing just because of your understanding, so that you will be able to understand it easily, right? That what logics are used here. Then let us prove the closure under addition. We will take x plus y, and we will show that this x plus y is still belonging to the set V, right? So x plus y, how does it looks like? It will looks like this, right? Now see, this is a sequence, and what we know by the algebra of sequences, that if xn converges to L, yn converges to m, then xn plus yn will converge to L plus m, right? This is my algebra. This is the result of algebra of convergent sequences, right? What I have discussed few minutes ago, right? So we will use it here, right? By algebra of sequence we get that xn plus yn will converge to this one, right? Now see, since L is real number, m is real number, so their addition will also be real number, right? And we know that if this is, this is obvious now, that in a real number, if you add any two number, then you will get a unique number, right? So that's why L plus m will also be unique, right? Now see, then since xn plus yn is a sequence, right, and it converges to this point, right? Xn plus yn is convergent, this converges to there, right? What does it mean? Xn plus yn is a convergent sequence, and since xn plus yn is a convergent sequence, it implies that it will belongs to V. Why? Because V is the set of all convergent sequence, right? So it implies that xn plus yn belongs to V. So we have taken two elements x plus y and we have shown that this x plus y belongs to V. Right? So what can we say? That V is closed under addition. Right? Clear? Now we will prove for the scalar multiplication. Right? See, closure under scalar multiplication. What will we do? At first we will take an element from V and another element from the field R. Okay, why? Because the field is here real number. Right? So let us take, let x belongs to V. Right? Then how does this x will look like? It will, then x will be equal to xn, where xn is convergent, and since xn is convergent, it implies that it will converge to a real number. Right? Say it converges to L. Okay, then we will take another element alpha from R. Right? Then we will do this. See, by the algebra of sequence we get alpha into xn will converge to alpha L. Right? This result is also discussed. Right? So we are using that here. Okay, see, basically what are we doing? We are just using the results of sequences just to prove this. Right? So what does it mean? It means that alpha into xn belongs to V. Why? Because this sequence is converges to this one, and this is the set of all convergent sequence. That's why this will belongs to V. It implies that V is closed under scalar multiplication too. Right? Now we will prove the four conditions under addition and four conditions under scalar multiplication. Only then our work will be over. Right? So let's prove the four conditions under addition. Right? Vector space property 1, commutativity. Right? So how can we prove? At first we will take two sequences. Right? Then we show that xn plus yn will be equal to yn plus xn. Right? See, let xy belongs to V. It implies that xn and yn is convergent. Right? See, since xn and yn are sequences of real number, and we know that real number satisfies commutativity, that's why this sequence will also commute. Right? So this is my logic, and I know that you did not understand that. How can we get it? Right? For that I am going to give you an example. Right? Suppose xn is my this one, right, and yn is my this one. Right? See, basically these are my real numbers. Right? Now if we add these two sequences, then what we get? We get xn plus yn, which will be equal to this one plus this one, then this plus this plus this plus this, and so on. Right? Then add them. What you get? After adding you will get this one. Right? Now add yn plus xn. Right? And see what happens. After adding yn plus xn, you will get 1 plus 1, this plus this, then this plus this, 1 by 2 plus 2, then 1 by 3 plus 3, and 1 by 4 plus 4. Right? And see, you get the same result. Right? That's why I am written here that since xn and yn are sequences of real number, and we know that real number satisfies commutativity, that's why this condition will hold. I hope after looking to the example you will be able to understand that why I have given this logic. Right? See, there may be other methods to prove it. Right? But this is also one of them. Right? So if you want, then you can go beyond it. It will be beneficial for you, and I will be happy with that. Right? So in the similar way, we can say that since in the set of real numbers associativity holds, that's why associativity will also satisfy. Right? So till now what we have proved? We have proved that V is a set of convergent sequence, and V is closed under addition and scalar multiplication, and we satisfied commutativity and associativity under addition. Right? Now what we have to prove? Now we have to prove identity and inverse. Right? So let's prove it. Vector space property 3, identity. Right? And what we know about identity? Suppose, wait, see, let x belongs to v, it implies that x equal to xn is a convergent sequence, right? Now see, we are taking another sequence, right? Since we know that every constant sequence is a convergent sequence, I have told it earlier, right? So we are going to use that one. Since we know that constant sequence is convergent, right? Know that every constant sequence is convergent, right? Right, precisely, because we are mathematician, right? Since we know that every constant sequence is convergent, right? So we can take any constant sequence, so we are choosing this one, right? So this is also a sequence, right? This is constant sequence and this is convergent, right? Let us give a name to it. Suppose this is my sequence, right? I have given this sequence name as 0. You can give it any other thing, no problem. It is just a notation, right? So we have taken a sequence which is convergent, this one, right? Now since this is convergent, so it will belongs to V, right? And see, if we add any sequence with it, right, then we will get that sequence, right? And we know that 0 plus xn is equal to xn, right? And similarly we can show that xn plus 0 will also be equal to xn. What does it mean? It implies that 0 is identity, means this one is identity sequence, right? So we have get that there is a sequence which is identity, this one, right? So I think many of you may be confused here also, right? That's why I am going to give example here. Suppose xn is equal to n, which is equal to 1 2 3 dot 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 dot, right? And here 0 is my sequence, this one, 0 0 0 dot dot dot, right? Now add it, xn plus 0, what it will be? It will be 1 plus 0, right? 2 plus 0, 3 plus 0, and so on. It will be 1 2 3 dot 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 dot, which is equal to this one, which is equal to xn, right? Similarly we can show it for this one. So we have proved the identity, right? Now we will prove inverse. So let us prove it. This will be Vs for inverse, right? So let us consider that x belongs to V. It will imply that x equal to xn is a convergent sequence, right? And let xn converges to L, right? Then by algebra of sequences, we have seen that if xn converges to L, then minus xn will converge to minus L, right? This result we have seen earlier, so we are going to use it here, right? By algebra of sequence, we have minus xn will converge to minus L, right? So see, since minus xn is converging to a real number, it means this is convergent sequence. Since this is a convergent sequence, so this minus xn will belongs to V, right? So for each xn in V, for each x in V, there we get another sequence in V, such that if you add them, xn plus minus of xn, what will we get? We will get 0, means identity. What does it mean? It means that this is my inverse, right? Similarly we can show that minus xn plus xn, this will also be equal to 0, right? So from here what we can conclude, that minus xn is inverse, right? Hence inverse exists, therefore inverse exists. So what we have proved that if V is a set of real sequences, then this is closed under addition, this is closed under scalar multiplication, and under addition it will satisfy commutativity, associativity, identity, and inverse. Now we have to prove these for one, right? So let's do it. How can we prove it? Right, vector space property 5. So see, let x belongs to V, it implies that x equal to xn is convergent, right? And see, one is from field, right, means one is from R, okay, and we know that 1 into anything will be equal to that thing, right? This is obvious, right? So don't worry about that, just write it, hence it is proved. Okay, see, this is a sequence of real number, right? 1 into any real number will be equal to that number, right? You can think like that also, right? So next one, now we will prove this one. So see, this is basically real number, right? And we know that associativity under multiplication holds in real number, that's why this condition will also satisfy, right? So see, let x belongs to V, it implies that x equal to xn is convergent, right? And AB belongs to R, where R is a field. Then since associativity under multiplication holds in real number, so it will imply this condition holds, right? See, I have given you example, right, for identity and inverse by taking examples like xn equal to n or yn equal to 1 by n, right? So take xn equal to n, then a and b anything, okay, then try to do it, right, so that you will be able to understand it in a better way, right? This is your homework, okay, this is your homework. Try to do that with example yourself, right? Only then you can improve yourself, right? So we have remaining two conditions to prove, right? So let us prove it. How can we prove this one, right? At first we will take two elements x and y from the set V, right? And then we will show this one. We will start from here and we will show this, right? So let x and y belongs to V, it implies that x equal to xn is convergent, y equal to yn is convergent, right? And a belongs to R, right, where R is field, right? So take LHS, this equal to this, right? Now we are putting x and y, we get this, right? Now we will add this sequence, then we will get a into xn plus yn. Now see, since we know that distributive property holds in R, right? Now the question arises that why we are using the distributive property in R, though we have the elements from the set V and R. So see, this is from my real number, right? And these are my sequence of real number, right? What does it mean? It is a sequence of real number, it means that each term is from real number, right? So though you are taking it from the set V, but basically this is from real number, right? So that's why this is real number, this is real number, this is real number, right? So we are using the property of real number, right? So we are using the distributive property. Since distributive law holds in R, by using that we get this one, right? Now we will do the simplification, this one, okay, then we will take a common, then we will get this one, and then xn yn is equal to x and y. Therefore this condition holds, right? Just remember my word, what I am saying, right? Only then you will be able to think, right? And if you don't understand, then just pause the video, right, and think, then proceed, right? At first clear your doubt, then proceed, and still you are not able to make it clear, then please comment, right? Then I will make a reply to you, right? So next, VS8, right? This one, how can we prove? At first we will take one element xn, x from V, where x is convergent, and AB from R, where R is field, right? Then we will take LHS, this one, we will put the x here, right? then we know that since distributive property holds in R, basically this is real number, this is real number, and this is also real number, right? So we will get this, after that we will get this, therefore this condition holds, right? Oh wait, actually there I have written something, let it erase. There is no work of y, right? So let's remove it. X belongs to B. Okay, so we have proved that V is a set of all convergent sequence, right? And it satisfies closure under addition and scalar multiplication, and commutativity, associativity, identity, and inverse under addition, and 1 into x equal to x, and remaining 3 properties, right? That's why we will say that this V is a vector space, and hence this completes our proof. This completes proof, right? So this is the way that whenever you have given a set, and if they say that so that this is a vector space, then you have to do this, right? And sometimes you will get questions like check whether that this set is a vector space or not, right? And in this case, and in that case, if you can find any one property that is not satisfying, then you will able to say that no, this set is not a vector space, right? We will do all kind of questions, right? We will cover semester exams first, right? At first we have covered basics. Now we are covering the semester exams, right? After that we will cover competitive exams like IIT JAM, CSIR NET, GATE, TIFR, NBHM, ISI, each and every questions, right? Though it will take time, but we will cover it, right? So be patient, this is a very long journey. Okay, so next, what it is saying that so that the set of all real valued continuous differentiable or integrable functions defined on the interval 0 to 1 form a vector space over the field of real numbers, right? Basically here are two questions, right? That we have to show that the set of all differentiable functions form a vector space, and set of all integrable functions forms a vector space over this interval, right? So at first we will show it for the integrable functions, and after that we will do it for the differentiable function, right? So let us consider a set V where V is the set of all integrable functions defined on the interval 0 1, right? See, let V equal to this one f such that f is integrable on 0 1, right? After that we will take two elements from this set V, right? So let f and g belongs to V. So how does this f and g will looks like? It will looks like this, right? Integration of 0 to 1 fx ds exists, and integration of 0 to 1 gx dx exists, right? Now we will show that it is closed under addition and scalar multiplication, right? And we will show it by using the property of definite integral, right? So see, now f plus g equal to, how does it will looks like? It will be equal to this one, right? And by the properties of definite integration we can separate it, so do it, right? From where we get it from the property of definite integral, right? See, we know that this one exists, right? And this one exists, right? By definition, okay? This one exists and this one exists, so their sums will also be exist, right? Since RHS side is existing, that's why LHS will also exist, right? It means that f plus g belongs to V, hence f plus g is closed under addition, right? Do you understand now? I hope you understand it, right? So next, scalar multiplication. Let a belongs to R, right? Then a into f, right, where f is a integrable function, so it will be equal to this. Now by using the property of definite integral we will get this, right? Since this is a real number, right? Since this is a finite real number, right? And this is finite, means this exists, so their sum will also be finite and it will exist, right? So a into f will belongs to V. Why? Because this is integrable, so this is integrable, right? So therefore B is closed under scalar multiplication 2, right? Now we will prove that this will satisfy 4 conditions under addition and 4 remaining conditions under scalar multiplication, right? So next, Now commutativity. See, how can we prove? At first we will take two elements from the set V. So let f and g belongs to V, right? So how does this looks like? It will looks like since f and g belongs to V, so integration of 0 to 1 fx dx exists, and integration of 0 to 1 g of dx exists for all x belongs to closed interval 0 to 1, right? Now 0 to 1 integration 0 to 1 f plus g over x equal to this we get by using the property of definite integral, right? And see, what is this? Actually f is a real valued function and g is a real valued function, right? And we are integrating it, right? So integration of fx from 0 to 1, what it will give? Actually it will give a real number, right? Similarly this integration will also give a real number, right? So real number plus real number, and we know that commutativity in real numbers is allowed, right? So we can write it like that, right? Why? Because commutativity in real numbers is allowed, right? So, and again by using the property of definite integral we can write this like this, right? So what does it mean? It means that f plus g is equal to g plus f. Therefore commutativity holds, right? Wait, how we are getting? By using the property of definite integral, right? And similarly here, right? And this we get from commutativity in R, right? Why? Because this belongs to R and this belongs to R, right? So this satisfies commutativity, right? Now we will do it for associativity in the similar way, right? So I am doing it here. Wait, let us erase it, right? So associativity. Right? So at first let f, g and h belongs to V, right? What it imply? It will imply that integration 0 to 1 fx dx exists, right? And integration of 0 to 1 gx dx exists, right? And integration of 0 to 1 hx dx will also exist, right? Now what we do? Integration of 0 to 1, at first we will do it for f plus g, then plus h dx, right? What it will be? It will be equal to, by using the property of definite integral, and after doing all of these things we will get integration of 0 to 1 f plus g plus h of x, right? And by this way we can show that therefore f plus g plus h will be equal to f plus g plus h, right? So associativity will also hold, right? Now how does this come, right? So at first you will apply the commutativity here, right? And by then you will get g plus f, right? And after that, by thinking it as a one element, right, as a single integration with h, you can get this, right? So do it by using this concept, right? This you have to do it yourself, right? Just think and do, and let me know that you are able to do it or not, right? So comment, right? I will wait for your comment, right? So the next is identity, additive identity, right? So we know that every constant function is integrable. Every constant function is integrable on a closed and bounded interval AB, right, where AB belongs to the set of real numbers, right, and we know that 0 is a constant, right, so integration of 0 from 0 to 1 will also exist, right, this will exist. Wait, so integration of 0 to 1, 0 of dx will also exist. Why? Because we are using the result of integration, right? See, we are doing each and everything by using the result and properties of integration, right? So this will also exist. And now let f be any function from the set V, right? So do it. Integration of 0 to 1 f plus 0 over dx, what it will be? It will be break, like integration of f of x dx plus integration of 0 to 1 0 of dx, right, what it will be? It will be integration 0 to 1 fx dx, right, plus 0, which will be equal to this, right, 0 to 1 f dx, right. So see, we got an additive identity, right, this is my additive identity, right, so additive identity exists, right, and similarly we can show it for integration 0 to 1 0 plus f equal to f, integration of 0 1, right. So additive identity exists. Now we will show it for the inverse, additive inverse, right. So do it, additive inverse, right. See, let f belongs to V, right, so it implies f will 0 to 1 f of x dx exist, right. And again, by using the property of integration, we know that if f is integrable, then minus f will also be integrable, right. What does it mean? Since minus f is integrable, means it will also exist. We are getting it by using the property of integration, right. This will also exist. What does it imply? It implies that minus f will belongs to V, right. Now check, integration of 0 to 1 f plus minus f dx equal to bracket 0 to 1 f of x dx plus 0 to 1 minus f of x dx, right. Now bracket 0 to 1 f of x dx minus, by using the property of definite integral, we can take the minus outside, and plus and minus will be equal to minus 0 to 1 f of x dx, right, and this will be equal to 0, right. Hence additive inverse also exists, right, and we can show it for 0 to 1 minus f plus f x dx also, right. So we have proved that this was the set of all integrable function on 0 1, right, and we have at first we have showed that this is closed under addition, then we have showed that it is closed under scalar multiplication, then we have proved that this will satisfy commutativity, associativity, identity and inverse under addition, right. Now we will show these four properties, right. So let's do it. So see, scalar multiplication. What was the first property? The first property was 1 into x equal to x, right. So let 1 belongs to the field R, okay, and f be any element from the set V, right. So see, let, sorry, this is not a, this is 1, right, make it correct, 1 belongs to R field, okay, and then f belongs to V, it implies that integration of 0 to 1 fx dx exists, right. Now integration of 0 to 1 into f x dx, it will be equal to 1 into this by using the property of integration, right, and 1 into anything will be equal to that thing, right. So we are writing this, right. So what we get? We get that 1 into f equal to f, right. Now second one, What was the second one? The second one was ab into x equal to a into bx. Right, so see, let ab belongs to R where R is a field and f belongs to V, implies this exists. Right, now see, now 0 to 1 integration ab of f of x dx equal to, right, at first we will take it outside by using the property of integration. Right, now again take the b inside, right, this one, and it implies that ab into f equal to a into bf. Right, do you understand each and everything now, each and every concept, and right, that what logic you are using and what result we are getting. Right, see, next one, what was next? This was let a belongs to R, right, and fg belongs to V. What does it imply? It implies that this one exists. Right, then next page, wait, let me make it correct. Right, this is actually 1, not a, right, see, this is 1 belongs to R. Right, now next, so see, after that, now we can write it like that, c into f plus g. What was the property? That a into x plus y equal to ax plus ay. We are actually proving that one. Right, so c into f plus g of x dx equal to, we will take the c outside by using the property of integration, then we can break it by using the property of integration. Right, now we'll multiply it individually. Right, this one, right, so what we get? We get that c into f plus g equal to cf into cg. Right, so next one, what was the next one? The next one was a plus b into x equal to ax plus bx. Right, so a plus b belongs to R where R is a field. Right, then f belongs to V, which implies that this one exists. Now a plus b into f, so a plus b into f x dx equal to, we can take it outside by using the property of integration. Right, then we will multiply it separately, a into this one and b into this one. Right, now take it inside, take the a inside. Right, so what we get? We get this one. Right, so all the properties, all the 4 properties under the scalar multiplication also satisfied. Right, so therefore you can write, so see what we done, we do that, there was a set, right, then it was closed under addition and scalar multiplication, then it satisfies all the 4 conditions and all the 4 conditions. Right, what does it mean? That B is a vector space over the field real number. Right, so this was the proof. Right, so proved. So this is the way to prove. Right, so next, what was next? We have to prove that set of all differentiable function forms a vector space. Right, so this will be homework for you. Right, I have proved the set of all integrable function is vector space. Right, and you have to prove that set of all differentiable function is vector space. Right, so how can you prove? At first you will take a set, right, set of all differentiable function, then you will take 2 elements from here, then you have to show all the properties step by step. Right, and you have to use the properties of differentiation here. Right, so use it and prove it. Right, this is your homework. Right, so next, what it is saying? It is saying that so that the set of matrices forms a vector space over the field of real numbers. Right, so how can we prove it? At first we will take a set V, right, where V is the set of matrices, then we will take 2 elements from that set, then we will prove that this set is closed under addition and scalar multiplication, then we will prove the remaining conditions. Right, so let's begin. Let B, right, where B is the set of all matrices of order m cross n. Right, at first we will prove that this is closed under addition. Right, so see, let AB belongs to V. right? What does it imply? It implies that A will be a matrix of order m cross n, and similarly B will be a matrix of order m cross n, right? Now we will check the addition. Now A plus B equal to what it will be? It will be this, where a₁, a₂ and b₁, b₂, all of these are from set of real numbers, right? So we can write it like that. Now by using the addition of matrices we will get this one, right? And since all A and all B are belonging from the set of real numbers, so their addition will also be from the set of real numbers, right? And the order of the matrix and the order of the matrix will be m cross n, right? So what does it mean? That A plus B will also belongs to the set V, right? What does it mean? It means that V is closed under addition, right? One part has been proved, right? Now the second one, scalar multiplication, right? So see, so at first we will take an element from the field, right? And we will take an element from the set V, right? Then we will show it. So let A belongs to R, where R is a field, right? Then we will take an element A from V. What does it imply? It will imply that A will be like of this form, right? Now A into capital A, it will be equal to this, right? It will be in this form, right? Now by using the matrix operation we will get that this A will multiply with all the elements inside the matrices, right? So do it. We have done this, right? And see, this is a real number and this also is a real number, right? So their product will also be a real number. What does it mean? That we are getting a matrices, right, of real numbers of order m cross n. What does it imply? It implies that this belongs to the set V, right? And hence this will also belongs to the set V, right? So see, and therefore V is closed under scalar multiplication, right? Now we will prove the remaining conditions, right? So at first under addition we will prove commutativity, right? So let AB be any elements from the set V, right? So A plus B will be equal to of this form, right? And it will be equal to this form, right? And then we know that a₁ and b₁, all of these are from the real numbers, right? And we know that commutativity in real numbers is allowed, right? So we can write it like that, right? And after that we can separate it, right? And what we get? We get this one. It implies that A plus B equal to B plus A. It means that commutativity holds, right? Now associativity. See, it will hold. Why? Because associativity holds in matrices, right? From using that property we can say that associativity will satisfy, right? See this one, right? Now we will prove the identity, right? So obviously you can see that any zero matrix will be the additive identity element, right? If you add any zero matrix with any matrices you will get that matrix, right? So see, let B equal to this one, then A plus B equal to this one, right? Which will be equal to of this form, and this will be equal to this, and this is equal to A, right? I hope you can understand, right? Now we will go for inverse, right? Additive inverse, right? So see, how can we find? So at first see that let A be any matrix, right? Since A belongs to B, it means that A is a real matrix of order m cross n, right? And the entries of that matrix is from the real number, right? What does it mean? That each element of that matrix is of real number, right? And we know that for each real number there exists additive inverse for that in set of real number, right? So we can see, wait, I am writing, let A belongs to B, it implies this one, right? And see, since all Aij belongs to R, right? and we know that in the set of real numbers, for each element there exists its additive inverse element. Like if there is 1 in R, it means -1 is also there. If there is 10, then -10 is also there. And similarly for rational and irrational numbers also, right? So it implies -aij belongs to R, right? By taking this -aij, we are making a matrices, right? So we are making a matrices by taking these aij, right? This -aij. Now we will take minus common from here, right? So take it. Wait. After taking minus, we will get this, and we know that this is equal to a, right? What does it mean? It is equal to -a. It means that for each a in V, there is a -a in V also, right? What we are getting? We are getting that, wait, we are getting that for each a belongs to V, there exists -a belongs to V, such that you can add a plus -a, which will be equal to 0, right? And hence we can say that for each a there exists its inverse -a, right? So V is closed under addition. Sorry, V is closed. Sorry. So we can say that for each a in V, there exists a inverse of it, right? So what we have done, at first we take a set, right? Then we have showed that this is closed under addition, this is closed under scalar multiplication, this satisfies commutativity, associativity, identity and inverse, right? Now we will prove this remaining 4 conditions, right? So see, wait, what was the first property? Let me write it. See, let 1 belongs to R and a belongs to B, right? Then we can say that 1 into a, right? What it will be? It will be equal to this one, right? Now we can multiply 1 with each element, right? So do it, this one, and we know that this will be equal to this, and this is equal to a, right? Hence this property holds, 1 into a equal to a, right? Now the second one, let AB belongs to R and A belongs to V, right? Now AB into A, it will be equal to of this form, right? Now we will multiply the V, right? We will take it inside, right? So do it. By taking that, we will get this, right? And now we can write it like in this way, right? So this condition also holds, right? So next one, see, let C belongs to R and AB belongs to B, right? Now we will start from this, right? And this will be equal to this, right? I hope you will understand, right? So I am just writing it, okay? Just see, and this will be equal to this by using the usual matrix addition, right? Now we will do this, right? I hope you understand each and every step, right? Now we can write it like that, okay? After that we will do that. We are just separating the things, right? And after this we will get this one, right? And this is equal to A and this is equal to B, so we will get this one, right? So this condition holds, right? Now there is only one remaining condition, so let's prove it. Let CD belongs to R, where R is a field, right? And A belongs to B. Now this one and this will be equal to this, right? I hope you will understand, right? Just go through it. Then we can multiply it, right? Then we can do it, right? After that we will separate it, right? Then we are taking common, then we will get this. After that we can get this, right? And hence this holds, right? So finally we have completed all the properties, right? So see what we have done. We have taken a set V, right, and we have shown that this is closed under addition and scalar multiplication. Then we have shown that this satisfies these four properties: commutativity, associativity, identity, and inverse, right? Then we have shown that it satisfies the four properties under scalar multiplication. So it implies that this set V is a vector space over the field F, right? So this is the way to prove what it is saying. It is saying that let R be the field of real numbers and let Pn be the set of all real polynomials of degree at most n. Then prove that Pn is a vector space over the field R. Right. So let's do it. At first we have to construct a set, right? So what is V here? Here V is given by Pn, right? So write it. See, here V is given by Pn. So let V equal to Pn, and we know that Pn is defined as a₁ plus a₁x plus a₂x square plus dot 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 so on, and plus the last term xn an, right, where a₁, a₁, a₂ dot 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 an belongs to the field of real number, right? So now this is the set, and we have to prove that this set forms a vector space, right? So what we have to do, at first we have to take two elements from here, right? Then we have to show all the conditions, right? So see, let P of x and Q of x belongs to V. What does it mean? It implies that P of x will be equal to of this form. Suppose P of x is equal to a₁ plus a₁x plus a₂x square plus dot 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 plus an(xn), right? And Q of x is equal to b₀ plus b₁x plus b2x square plus dot 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 plus bn(xn), right? Where a1 to an belongs to the real number and b1 to bn belongs to the real number, right? Now we have to show that this is closed under addition, this is closed under scalar multiplication, and we have to prove all the remaining conditions under addition and all the remaining conditions under scalar multiplications, right? So do it yourself. This will be your homework, right? Do it yourself. This is very easy, right? See, I am giving you a hint, right? So what will be the identity under addition? Identity will be the zero polynomial, right? And inverse will be for each polynomial p of x, there always exists a polynomial minus p of x when you multiply it with -1, right? So use it and do it yourself. Okay, next. Now what it is saying? It is saying that identity element and the inverse element of a vector space is always unique. Okay, so this is basically a theorem, and now we are going to prove it. Okay, so let's begin. At first we will prove the identity. So how can we approach? At first we will let that there are two identity of a vector space. So let 0 and 0 dash be the identity element of a vector space V, right? Since 0 and 0 dash is an identity element, so by using the identity property we will get x plus 0 and 0 plus x will be equal to x for all x belongs to V, right? Similarly, we will get for 0 dash that x plus 0 dash equal to 0 dash plus x equal to x, right? Now from equation 1 and 2, what we get? We will get this one, right? By now using the cancellation law, we will get this one, right? So see, what we let? we let that there are two different identities. There are two different identity elements. Okay. And now we have proved that those are same. Okay. What does it mean? It means that identity is unique. So similarly, we will do it for inverse. Okay. So see, there is nothing to express. I am just writing. Okay. Just go through it. You will be understand each and everything. Okay. So next. So see, till now we have seen that set of convergent sequences, set of differentiable and integrable functions, set of polynomials degree up to n, and the set of matrices forms a vector space. Okay, and we have seen some theorems and results and few examples which forms vector space. Okay, now we will move to the questions. Okay, what kind of questions? Basically, you will have a set. Okay, and you have to check whether that this set forms a vector space or not. Okay, so what should be your approach? Right, so see, I am writing here approach. Okay, whenever you find such kind of questions to check whether that a set is a vector space or not, then remember this approach. Okay, at first always construct the set. Okay, construct set. Okay, construct V. Then try to find any one vector space property that fails. Okay, this is very important. Right, after constructing the set V, try to find any one vector space property which fails. Okay, and if you find such kind of property, then definitely you will conclude that this set does not form a vector space. Okay, and if no property fails, then the set will be a vector space. Okay, so always try to check those properties which you think that it may be failed. Okay, or it has a higher chance to be failed. Okay, always try to go with that properties first. Okay, so let's move to the questions. What it is saying? It is saying that let V be the set of all pairs xy of real numbers. Okay, and let F be the field of real numbers. Defined this condition and this condition. Okay, now it is asking that is V with these operations a vector space over the field of real numbers. Right, so what is given? At first you have to construct the set V. Okay, so write it. What is given? Given that V is equal to xy pairs of real number. Okay, what does it mean? It means that x comma y belongs to the set of real number. Okay, such that these two conditions. Okay, so write it xy plus x1 y1. Okay, x1 comma y1. Okay, it is equal to, how is it defined? It is defined as x1 plus x2 and the second tuple is 0. Okay, and what is the second condition? This one, it is just like this. Okay, c into xy equal to cx of 0. Okay, so this is my set V. Okay, now we have to check whether that this set V forms a vector space or not. Okay, so step 1 we have done. Okay, now we will move to the step 2. Okay, what is the step? Now see, check the conditions. Basically, what will you do? You will take any two elements from this set V. Okay, then you will check that whether that this set V satisfies these conditions or not. Okay, 1 2 3 4 and here 4 conditions. Okay, so what I have said, at first try to find that condition which may be fail. Okay, So see, at first look at this condition very carefully. Okay, this one, right? This is basically related to the scalar multiplication, right? Why? Because C is from the field, okay, and xy is a vector. Okay, so this is basically scalar multiplication, right? See how to think throughout the questions, right? This is the work of mathematician, right? You will have given some questions, right? From the given data you have to reach to your solution, right? So see, what is this? This is scalar multiplication, right? And we know that under scalar multiplication there are few conditions. What conditions? The first condition was 1 into x equal to x. Second was ab into x equal to a into bx, right? Just think like that, okay? And there was, what was there? There was a into x plus y equal to ax plus ay, right? And the last one was a plus b into x equal to ax plus ax plus bx. Okay, so now think, see what it is. It is c into xy equal to this one, right? So at first we will check this property, right? Why? Because it is easy, right? So see, 1 into, now at first let t belongs to v, right? Since t belongs to b, it implies that t will be equal to something like ab, right, where ab belongs to r. Okay, now see, we will multiply it with 1, right? 1 into t. What it will be equal to? It will be equal to 1 into t is equal to a into b, right? And this is equal to, by this operation, see how is it defined, that the c will be multiplied with the first tuple, right? So multiply it. This is 1 into a, right? And the second one is 0, right? 0. So what it will be? It will be equal to 1 into a equal to a, right? And 0. So what we get? Implies we get 1 into t equal to 1 into ab, right? Which is equal to a comma 0, right? Now remember the condition. What was the condition? The condition was 1 into x equal to x, right? If you multiply any vector with 1, then as a result you will get that vector, right? This was my property. So check whether you are getting or not. You are multiplying t with 1, okay, and you are not getting t. This is not equal to t. Is it equal to t? Means is it equal to ab? No, right? I think you may get confused, so just see what you have done. You have basically 1 into ab is equal to, it should be ab, right? Because 1 into ab, it should be ab, but it is not ab, it is a0, right? So this condition 1 into t is equal to t, this condition does not satisfy. That's why the set V is not a vector space over R, right? So this is my solution. Okay, see, you don't need to check all the properties every time. Okay, always approach like that. Now what it is saying, see, let V be the set of all pairs xy of real numbers and let F be the field of real numbers. Examine in each of the following cases whether V is a vector space over the field of real numbers or not. Okay, so we have to check that these are forming a vector space or not. Okay, so let's begin. At first, number one, what it is saying, there are two conditions, right? This one and this one, right? So we will start for the scalar multiplication first. Okay, so what it is given, this one, right? It is given that C of xy equal to C of x and C of y, right? So how many conditions are there under scalar multiplication? 4 conditions, right? See, I am writing here vector space under addition under scalar multiplication. Okay, there were 4 conditions and there were 4 conditions, right? What was the first condition? 1 into v equal to v, right? Then second was ab into v equal to a into bv. Okay, and the third one was a into v plus, let us another vector w, it will be equal to ab plus aw, right? And the last one was a plus b, which is a scalar, into v equal to ab plus bv. Okay, so let's check one by one. See, 1 into v, c will be equal to 1, so 1 into, this is my v, xy is v, right, vector, it will be equal to, see what it is saying, that c will be multiplied with the first tuple, right? So multiply it, 1 into x, it will be x, and the second will be as it is, right? Y will be y, right? So see, the first condition has been satisfied. Okay, it means that 1 into v equal to v, right? Now we will check this one, and I think this will also satisfy, right? Now we have to check the remaining 2 conditions, right? See, here we have to take 2 vectors, right, u and v, but here we have to take only one vector, right? So comparing to this one will be easier to calculate, right? So we will do it first, right? After that we will check this one, right? So see what it is, a plus b into v equal to ab plus bv, right? I am writing here, wait, what is the condition? A plus b into v, right? What is the v here, right? X plus y, sorry, xy, right? It should be equal to a into xy plus b into xy, right? Actually this is v, right? Here v is this one vector, right? A plus b into v, it should be equal to ab plus bv, right? This is our last property, so we are going to check it. So see, a plus b, at first we are doing LHS. Okay, so a plus b into xy will be equal to, see, how does it define that? C will be multiplied with the first one, so instead of c, what is here? A plus b, so a plus b will be multiplied with the first one, right, x, and the second one will be same, it will remain same, right? So our LHS is this one. Now we are doing for RHS, right hand side. Okay, it will be, we are calculating this one, right? So a into xy, what it will be? It will be equal to a into x, a will be multiplied with the first one and the second one will be the same. And now do this, b into xy, it will be equal to ax and y, right? So we get this one and this one. Now we will add it, right? Add it, then what will you get? You will get ax comma y plus, sorry, it was b, sorry, b into x, right? So bxy plus bxy, right? What it will be? It will be equal to ax plus bx, right? And this will be y plus y, right? It will be equal to take here x common, so it will be a plus b into x and 2y, right? This is my RHS. Now check whether LHS and RHS are equal or not, right? So here is, this is my RHS, a plus b into x and 2y, right? This is my RHS. See, is it equal? Yeah, first tuple is equal, but what about the second tuple? Here is y, here is 2y. What does it mean? This is not equal to this one, right? It means that this property does not hold, right? So we find a property which fails. What does it mean? It means that this will not form a vector space, right? Therefore not a vector space, proved, right? So this is the approach. Now what about second one? See, what about this x1 plus x2, x2 plus y1, right? So if you want to check, then you can check under addition, right? I think commutativity under addition will not satisfy, right? And associativity also will not satisfy. Commutativity and associativity, it will not satisfy. Just go through it, check it. This is your homework, right? And what about that? See, here c into xy equal to cxy, right? C was multiplied with the first one and the second one was same, right? And in this case c is multiplied with the second one and first one is same, right? So when you calculate in this similar manner, you will get that instead of here 2y, here will be 2x, and here the condition will be like that. Okay, so clearly you can see that this condition will not hold here, right? So this is also not a vector space, right? What about this one? See, x1 plus y1, x2 y2 equal to x1 plus x2 and y1 plus y2, right? So I think it will satisfy all the conditions, right, under addition. Now check this one, scalar multiplication. What it is saying? C into xy equal to cx square comma c square y, right? So at first check the first one, right? So see what it is saying, that c, let's choose that c is equal to 1, then it will be 1 into xy, right? What it will be? C will be multiplied with c, right? C means 1 into x square, right? X square. And the second one is c square means 1 square into y, right? What it will be? It will be equal to x square y. So what we get? We get that I am writing here, okay? We get that 1 into xy equal to x square y, right? And this is not equal to xy. What does it mean? That 1 into v is not equal to v, right? So the first property fails. That's why this is not a vector space, right? I hope I am able to make you understand, right? Now what about the last one? So this is standard result, okay? Basically this is R2 space, and this will form a vector space. It will satisfy all the conditions, right? So check. This is your homework, third one, right? Just verify it will satisfy all the conditions, right? This will be your homework, and I hope you can do it easily. Okay, so next one, another one. See, don't be panic after looking at the question, okay? It may be seen that this question is very hard, but no, at first you have to go through it, right? So see what it is saying. Let V be the set of all three tuples of the form this one, okay? What are the conditions? With addition defined as this one plus this one equal to this one, and the scalar multiplication defined by this equal to this, right? Where c belongs to real number, x1, y1 belongs to real number. Then they are asking that which of the following is incorrect, right? Number A, V is not a vector space over there, means we have to check whether this forms a vector space or not, right? Then V is an abelian group under addition. This is a new term, group and abelian group. What it is, I will explain, don't worry about that. Right, what is the next? That additive identity of V is this one. V is not an abelian group under addition, right? Again, you don't know what is group and what is abelian group, right? So see, I will teach you, or I will tell what it is after few minutes later. Okay, at first let's do what is in our hand, right? So we have to check that whether it is a vector space or not, right? So let's begin. And see, there is another property, additive identity of V is this one, right? So at first we will check this one, right? If additive identity is not there, then we can say that no, this is not a vector space, right? That's why we are starting from here. So what it is given? It is given that V equal to, what is V? This is x, y, 1, right? Such that x, y belongs to R, right? And these are my conditions, right? So I am writing here conditions also. x1, y1, 1, right? Plus x2, y2, 1 is equal to x1 plus x2, y1 plus y2 and 1, right? And the scalar multiplication is defined by x1, y1, 1 equal to cx1, cy1 and 1, right? So these are my three conditions. Okay, so see, what kind of elements are there in V? This kind. All the three tuples where the last one is 1, right? So take, let it is x, y, 1, right? And it is saying that additive identity of V is this one, right? So what is the property of identity element? That if you add any element with the identity, then you will get that element, right? So we are letting this element and we are adding with this one, right? So what we get? We get that, see, we will check the conditions from here for addition, and for multiplication we will check from here, right? See, what is this? x1 plus 0, see, x1 plus x2, right? Then y1 plus y2 means this one plus this one, this one plus this one, y plus 0, and the last one will be same, 1 1 1 1 1 1, right? What it is? It is equal to x, y, 1. Yeah, you can see that this plus this equal to this. What does it mean? It means that this is an identity element, right? So this option is my correct. Option C is correct. Okay, now let's check the vector space. So for vector space, this is our V, right? Wait, this is our V. At first we have to check that it is closed under addition and scalar multiplication or not, right? So see, how does it define? It is defined that x1 plus x2, y1 plus y2 and 1, where x and y, x1, y1, x2, y2 both are from real numbers, right? So you are taking any two elements from the set V, you are adding it and you are getting this. See, since x1, y1 and x2, y2 are from real numbers, so their addition will be also from real numbers, right? So see, this is of the form, let us suppose this is x, this is y, and the last one is 1. Yes, this is of the form V, right? So this belongs to V. X plus y means this plus this belongs to V. What does it mean? That V is closed under addition, right? What about a scalar multiplication? C into this one equal to this one, and you can check that this will also belongs to this set V. Okay, what does it mean? That V is closed under scalar multiplication 2. Okay, so yes, Now under addition we have to check four property: commutativity, associativity, and identity. So let's do it. Commutativity, see, x1 plus y, let's see, this one plus this one equal to this one, right? Now we will add x2 y2 1 plus x1 y1 1, right? If you add, then what you get? You will get that this one plus this one means x2 plus x1, then y2 plus y1, right? And the last one will be 1 according to these conditions, right? And you know that x1 and x2 y1 and y2 are from real numbers. So in real numbers commutativity is allowed, right? So see, suppose this is a, this is b, right? So this was b, this was a, so a plus b equal to this one and b plus a equal to this one, and check that this and this both are equal. What does it mean? It means that a plus b equal to b plus a, means commutativity satisfied, right? Similarly you can check that associativity will also satisfy, right? And identity, yeah, we have checked that this is identity, so identity exists, right? What is the remaining condition? The remaining condition is my inverse, right? So what is the property of inverse? Listen carefully. What is the property of inverse? The property of inverse is that if you have an element, right, and if you are adding that element with another element, right, and as a result if you get the identity element, this is very important. If you get identity element, then you can say that this is my inverse, right? So what is inverse? Inverse is an element. Inverse is an element, right? What kind of element? After operating with any element, you will get the identity element, right? So see what we have. We have, let an element x1 and y plus there will be something equal to identity element. What is identity element? This one, 0 0 1, right? So what will we add here so that we will get this one? So see, x, so we will take minus x, y we will take minus y, right? And here it will be 1. Why? Here you can't take any other number. Why? Here if you take 2, here if you take 2, then what will happen? That it will be this and it will be 2, right? But see, 2 is not here. In the set V there are always this kind of tuple, right? So that's why you can't take here any other number other than 1, right? So we have to check, we have to take this one, right? So this is our inverse, right? So inverse exists, right? So under addition all the conditions are my satisfied. Now we have to check the remaining conditions under scalar multiplication. What was the first condition? It was 1 into v equal to v, right? So write it. 1 into x. What is x? X, y and 1, right? It will be equal to, how is it defined? That C will multiply with first and second and the remaining will be the same, right? So do it. It will be x, y and 1, right? So 1 into x is equal to this one, right? So the first condition satisfies. What was the second condition? AB into this one, x, y and 1. What it will be? It will be equal to A into B, x, y, 1, right? By using the associativity, okay? After that you will get A, multiply it, you will get bx, by and 1, right? Bx, by and the third one is 1, right? And will be equal to, now multiply it. So when you multiply you will get that A will be multiplied with the first one, so ABX, right? A will be multiplied with the second one, so it will be, wait, technical glitch, right? So it will be a by, and the last one will be 1, right? So you get this one. Now if you go like that, a into b into x y 1, right? So when you do it, you will get the same result, right? So this condition also satisfied, right? Now what about the third condition, right? Third one. What was the third condition? The third condition was a into x plus y is equal to ax plus ay, right? This was my third condition. So this was one vector, this was another vector. So take a, let the first one is x1 y1 1, and the second one is plus, here let us second bracket, okay, it is x2 y2 and 1, right? So do it. It will be equal to a into, add it, so this one plus this one according to the given condition we are doing, right? This will be y1 plus y2, and the last one will be 1, right? Now multiply it. What you get? You will get a into, a will multiply with the first one, so a is multiplying with x1 plus x2, right? A is multiplying with the second one, a into y1 plus y2, and the last one will remain same, right? So we are getting this one as my LHS, right? This is my L, H and S, right? Now we will do for RHS. Sorry, this one my RHS. What it is? That a into first one plus a into second one, right? So it will be a into x1 y1 1, right, plus a into second one x2 y2 and 1, right? So when you multiply, you will get ax1 ay1 and the last one is 1. Similarly you will get ax2 ay2 and 1, right? Now add them, this one plus this one, so it will be ax1 plus ax2, right, ay1 plus ay2, right, and the last one will be 1, right? Then what it will be? It will be equal to, a will be common, a into x1 plus x2, a into y1 plus y2, and the last one is 1, right? So see, this was my LHS, this is my RHS. So LHS equal to RHS, right? What does it mean? It means that the third conditions also satisfy, right? Now there is only one remaining condition. What was that? It was fourth condition. It was a plus b into x equal to ax plus bx, right? So let's check it. A plus b, we are taking LHS, okay? A plus b into x1 y1 1, this is my vector. So what it will be? It will be equal to, this scalar will multiply with this one and this one, right? So do it. This is my scalar into x, right? Again the scalar into y, sorry, this is y1, right? So x1 y1, okay, and the last one will be 1. This is my LHS. Now we will calculate the RHS, okay? So RHS, what is RHS? RHS is a into x, means a into x1 y1 1 plus b into x1 y1 1, right? So what it will be? It will be equal to, at first multiply, what you get? You will get ax1 ay1 1 plus bx1 by1 and 1, right? And when you add, you will get a of x1 plus b of x1, a of y1 plus b of y1, and the last one will be 1 according to the given condition. Okay, because the addition is defined like that, right? So when you take common, you will get, take x1 common, right? So you will get a plus b into x1, right? A plus b into y1 and 1, right? So see, this is my LHS, this is my RHS. Okay, so LHS equal to RHS. What does it mean? The fourth conditions also satisfy. So finally what we get, there was a set, right, which was closed under addition and scalar multiplication, and under addition it satisfies all the properties, and under scalar multiplication it satisfies all the properties. So V is a vector space. Okay, so let's go to the question. What it is saying, that V is not a vector space over R, right? V is not a vector space over R, but we have seen that V is a vector space. V is a vector space. So this option is cancelled, right? So now what is group and what is abelian group, right? So this is a new term to you. So see, this is nothing, you have already proved it. Okay, so what is group? So see, so a set V is called a group when a set V is called a group when V satisfies the closure property under that operation, right? After that, if it satisfies associativity, identity and inverse, right, then this V will call a group. What I have said, that a set is called a group. The first condition is that it should be closed under operation, right? Basically binary operation. It should be closed. A set is called a group if it is closed under a binary operation and it satisfies associativity, identity and inverse under that binary operation. Only then you will be able to say that this set is a group, right? Now when does this set will be called as a abelian group? It will be called as an abelian group if this will satisfy only one more condition. What? Commutativity, right? So see, this is my set, right? And if after being closed it will satisfy these three conditions, then this will be a group, right? And if it will satisfy one more condition, commutativity, then it will call a commutative group or abelian group, right? These are same, commutative group or abelian group. Okay, so see, you have already proved what, that we have already proved that B is closed under addition, right? And it is commutative, it is associative, identity exists, inverse exists. What does it mean? Because of these three conditions, associativity, identity and inverse, this is a group, and since it satisfies the commutativity also, so this B is a abelian group under the binary operation addition, right? Why? Because it is closed under addition and it satisfies all four conditions. So what we get? We get that B is an abelian group. B is an abelian group, right? And B is not an abelian group. This is wrong. Okay, so finally we have completed it. It was a beautiful question. Okay, so what is our answer? B is not a vector space. This is false because B is a vector space. B is an abelian group under addition. Yes. Additive identity, this, yes. B is not an abelian group under addition. False. Okay, so next one, what it is saying, this is a similar type of questions, just in the matrix form. Okay, what it is saying, that let S be the set of all matrices of the form this, with addition defined as this, and the scalar multiplication defined as this, right? Now you have to check that additive identity of S is this, additive identity of S is not this. Okay, and then we have to check whether S is a vector space or not. Okay, so we will start from identity element. Okay, so see, at first we will write V. right? So that we will get clarified that what kind of elements will be there. Okay, how is it? a₁+b, right, such that AB belongs to R. Okay, and how the operations are defined? It is defined as a₁+b plus c₁+d, right, which is equal to this one. So a plus c, this one plus this one, it will be same, it will also remain same, and it will be b plus d, right? And how does the scalar multiplication is defined? It is defined as k into a₁+b, right, will be equal to ka₁+kb, right? So at first we will check additive identity, right, whether this is a identity element or not. So check, let a₁+b plus this one 0,1,1,0, add it. What you get? You will get this plus this. A plus 0 means a, b plus 0 means b, and this will be same, right? See, this is same, right? So see, you have taken an element and you are operating with it and you are getting the same element. What does it mean? This is my identity, right? Yes, this is identity. Okay, so option A is correct. What about the second one? See, there is a catch. Additive identity of S is not this one, right? So check. See, do you think that this element will belong from this set? Just think, does this element will belong from here? No. Why? Because at this place there are 1 and here is 0, right? So this does not belongs to V, right? So it is not an identity element, right? And the option is saying that additive identity of S is not 0. Yeah, this is not. So this option is also correct, right? There are many students, they will do like that. They will a₁+b and they will add like that 0, 0, 0, 0, and they will, using this condition, they will get a₁+b, and they will be surprised that yes, this is also an identity. But no. Why? Because this is not an element of V. Okay, so next, does it form a vector space? So I am saying yes, it will form a vector space, right? So this will be your homework, you have to do it yourself. And if you are unable to do any questions, right, so comment box is only for you, right? Comment, I will make you reply and clear your doubt. Okay, so I am giving you a hint also, it will satisfy, right? S is a vector space over R and it will not satisfy. Okay, so do it. Next one. So what it is saying? Okay, see, instead of x and y they are using a and b. Okay, and what are the conditions? These are my conditions. Okay, so wait, oh, I think we are familiar with this relation, right? So we will start from here. Okay, so write it, C into a₁, a₂, and it is equal to C of a₁ and a₂, right? So we will check the last condition. What was the last condition? The last condition was a plus b into x will be equal to ax plus bx, right? So we are going to check it. We will start from LHS, right? So my LHS is a plus b into, sorry, okay, don't use a plus b, use here x plus y, right? Because a plus b is already in use. So it will be x plus y into a plus b, right? So see, what is the difference here? For the previous problem, we are treating a and b as scalars, right? But in this problem, here a and b are my vectors, and here x and y are my scalars, right? So I am mentioning here so that you will not be confused. Here a and b are from the vectors and x and y are from the field of real numbers, right? So don't be confused with it. Okay, sorry, it is not my a plus b, it is my ab, right? So it is my vector. So this is my vector and this is my scalar. Okay, and it will be equal to what it will be? It will be this one, right? So a scalar is multiplying with the first one only, and the second one is unchanged. Okay, so it will be x plus y into the first one, right? And the second will be as it is, right? So it is my LHS. Now what about RHS? So let's do it. Ax plus bx, right? So what is a? A is my x, right? A into x, what is my x? A b, right? Sorry, a b, right? Plus this one b into, what is b? Instead of b we have y, right? Don't we get confused with the notations, right? See, I have just changed the notation and you can see the speed. Right? So see, y into what is x? X is ab, right? It will be equal to x a. So x will be multiplied with the first one, x scalar, a vector, right? Second one will be same, plus y vector b, right? Now add it. What you get? You will get xa plus ya, right? See, check here. If you add this one, then first tuple plus first tuple, right? And what about the second? The second one will be the product of this one, right? So what will be the product? B into b, it will be my b square, right? So this was my LHS and this is my RHS. Now compare them. If you write here, take common, okay? So x plus y into a comma b square, right? This is and this is same, right? But this is not same. Why? Here is b and here is b square, right? So this is not equal. What does it mean? That this condition does not satisfy. Okay, means this is not a vector space, right? You can check that more conditions will fail, right? So check it at your side. Okay, it will also be your homework, right? So next one. Now what it is saying? Oh, this is a very nice question. Okay, and just because that this is something different, because this is defined something different. Okay, so see what it is saying. Basically this is the set, right? V is my this one, and define addition of elements of V coordinate wise. What does it mean? It means that additions are defined as coordinate wise. Means that if you choose a₁, b₁ plus a₂b₂, right, then coordinate wise addition means a₁ plus a₂ and b₁ plus b₂, right? So my addition is defined like that. Okay, and the scalar multiplication is defined like this one, right? What it is saying, that c into a₁ plus a₂ equal to 0 0 if c is equal to 0, and this one if c is not equal to 0. Okay, so we will check for this one. Okay, so let's do it. What was the conditions under scalar multiplication? Conditions were 1 into v equal to v. The second one was ab into x is equal to a into bx, right? And the third one was what it was? It was a into x plus y is equal to ax plus ay, right? And the last one was a plus b into x is equal to ax plus bx, right? We have to check all the conditions, right? So let's do it. 1 into v, if you put here 1, wait, let me change the color. If you put it here 1, right, so it will be 1 into a and a2 by c, right? So it will be equal to a1 and a2, right? So 1 into this one is equal to this one, so 1 into v equal to v is satisfied, right? Similarly, you can check that this will also satisfy, right? So now we will check this one. Why? Because this is less difficult than it. Why? Because it has more calculation, because there are two vectors. Okay, so see, a plus b into x, so we will use here x and y, x plus y into vector ab, right? What it will be? It will be equal to, see, yeah, how is it defined? The multiplication is defined as c into a1, right? Means a scalar into this one. So this is my scalar and this one, and the last one is what it is. Let me erase it little bit. Okay, yeah, see, it is a2 by c, so here is my b by c means this one, x plus y, right? So this is my LHS, right? This is my LHS. Now what about RHS? Okay, so let us check it. ax plus bx, so here ax, right, here x is my scalar, okay, and what is the vector? The vector is this one plus another scalar into same vector. Okay, now do it. It will be equal to, multiply it, x into a comma b by x, right, by using this condition, plus y into a b by y, right? Now add it. Okay, when you add, you will get this one. This is equal to xa plus ya, right? So take a as common, then it will be x plus y into a, right? And the second one is b by x plus b by y, right? And this is equal to x plus y into a, right? And it will be, take the LCM, it will be by plus bx, right? So this is my RHS. Okay, and this was my LHS. Now compare what you get. You will get this, yes, this one is same, but this is not same, right? So LHS is not equal to RHS, right? What does it mean? It implies that not a vector space. Okay, so this was the approach. Okay, and like that you can check each and every question, right, no matter what the conditions are given. Okay, see, basically these are the problems of very famous book Friedberg, right? This is a very standard book for linear algebra. Okay, so next one is saying let V equal to this one where F is a field. Okay, define addition of elements of V coordinate wise. Okay, so I think now you can understand that what is coordinate wise. Okay, and scalar multiplication is defined like that. Okay, so this is easy for you. Why? Because choose c equal to 1. Okay, means the first condition of scalar multiplication. It was 1 into v equal to v. Right, so check it. 1 into a1 a2 a1 a2. Okay, what it will be? It will be a1 0. Right, a1 comma 0. Right, a1 0. Right, so see, and this is not equal to v. Right, so vy this one. So see, we have multiplied 1 into this one and we are not getting this one. Right, so 1 into v equal to v, this does not satisfy. It means this is not a vector space. Okay, see how easy it is. Okay, just because you have understood the concept step by steps. Okay, so this is the way to read pure mathematics. Basically I am building your basics so that you can solve the questions from net and get very easily. Okay, so next, now what it is saying? It is saying that let B be the set of ordered pairs AB of real numbers, right? So that V is not a vector space over R with addition and scalar multiplication defined by this one. Okay, what it is saying? So that V is not a vector space, right? So we have to check that which condition fails. Okay, so let's do it. What about first one? See, it is k into ab equal to ka kb, right? I think this will not makes any problem. Okay, so focus on it. What it is? It is ab plus cd, okay, equal to, it is defined as a plus d b plus c, right? A plus d, this one plus this one, this one plus this one. Okay, so what was the first condition under addition? It was commutativity, right? So let's check it. See, this one plus this one equal to this one, right? So now we will check for cd plus ab, right? What it will be? It will be equal to this one plus this one, right? So this one plus this one means c plus b, comma this one plus this one means this one plus this one equal to d plus a, right? So see, is it equal? No, right? So commutativity does not satisfy. Commutativity fails. Okay, so that's why this is not a vector space, right? So I think you may be confused here, right? So I am going to take an example also, right? So don't worry, I will make each and everything very clear, right? Choose 1 0, right, and c to be 0 and d to be 1, right? So when you add, what will you get? A plus d, it will be 2, right? And b plus d, it will be 1, right? So this one plus this one equal to this one. Now here 0 1 plus 1 0, what it will be? This one plus this one, it will be equal to 0, right? And this one plus this one, this is equal to 2, right? So see, these are not equal. That's why commutativity fails, right? So let's move to the second one. What it is saying? It is saying that see, ab plus cd, a plus c, b plus d, right? So I think this will not make any problem. So we have to check here, right? What it is? It is k into ab equal to ab, right? So we will check this one. So 1 into b, it will satisfy. Okay, ab into x, I think it will satisfy. And in the case of second, there we have to take two vectors, right, which is more calculative. That's why we are taking the last one first, right? So what was that? It was x plus y into ab, right? It should be equal to x into ab plus y into ab, right? So where x and y are from scalars and a and b is my vector. Okay, don't be get confused with the notations, right? So let's start from LHS. What is LHS? See, this is my scalar. Totally, this is a scalar and this is vector. So how does the scalar multiplication is defined? That multiply anything with it, you will get this vector as a result, right? This is how our scalar multiplication is defined. So this will be equal to AB, right? This is my LHS. Okay, now let us work on RHS. What about RHS? RHS, it is x into AB. What it will be? It will be AB, right, plus y into AB. According to this condition, it will also be AB, right? Now add it. How does the addition is defined? Addition is defined tuple wise, right? A plus C, B plus D. So it will be A plus this one. So A plus A, it will be equal to 2A. B plus B, it will be equal to 2B, which is equal to 2. We will get as common, then it will be AB, right? So see, this was my LHS, this is my RHS, right? So LHS is not equal to RHS. Why? Because here 2 is multiplied with it, right? And here is only AB. So LHS is not equal to RHS, right? So this condition does not holds. That's why this is not a vector space, right? See how easy it is. Okay, only you have to make a correct approach. Only then you will get the answer in a very fruitful manner. Okay, and now what about 3? It is saying that A plus B plus C plus D equal to this and K into this equal to this. So you can see that this will not make any problem, right? So we will have to check here, right? So how that it is defined? It is defined as AB plus CD. It is defined as equal to 0, 0, right? So under addition, I think the commutativity will satisfy, and similarly the associativity also satisfy. So let's check it. See, this one plus this one equal to this one. Now we will check it for this, right? CD AB equal to what it will be equal to. Add anything. The addition property is defined so that whatever you add with this vector, you will get only 0 vectors, right? So this will be also equal to 0. Hence this plus this and this plus this is equal. That's why commutativity is satisfied, right? Similarly associativity will also satisfy. Now talk about identity. What about identity? See, identity means you have any vector, right? Identity is that element when you add with it, you will get this vector in back. Okay, but see, our addition is defined like that. Here will be always 0, right? In this position, except 0, there will not be anything else, right? So that's why add anything here, you will never get other thing except 0, right? So x plus identity equal to x, this property fails, right? So in this case identity fails, right? That's why this is not a vector space. Identity under addition fails. Okay, I hope I am able to make you understand very clearly. If not, then the comment section is only for you, right? Just write the question number in comment section. Just write the question number and timing, right? And then your doubt. Okay, and I will make you reply, right? So now next, what it is saying that AB plus CD equal to ACBD and K into AB equal to KA KB, right? So see, in this case it is okay, there is no problem. Now we have to check here what it is. It is AB plus CD is equal to AC BD, right? So let's talk about the commutativity. What about commutativity? When you add CD plus AB, it will be equal to this one into this one. So this one into this one, it will be CA, right? This one into this one, right? B into D. This one into this one, it will be DB. Since we are working in the field of real number, so commutativity will satisfy. So AC and BD, yes, commutativity satisfied. Okay, now check the associativity, and similarly you can check that associativity also satisfies, right? So now let's talk about identity elements. So what is an identity element? So identity element is a special kind of element. What type? Suppose you have a vector, right, and now you are adding it with another vector, right, and you are getting the same vector as a result, right? So this kind of vector is called identity. Okay, so see how is it defined? It is defined as this one, right? See, this plus this, it will define like this into this, right? So what element should we choose here so that the result will be this one, right? So see, if this is your vector and if you are choosing C and D as 1 and 1, right, 1 and 1, then as a result you will get this, right? A into this one equal to A, B into this one equal to B, right? So this is an identity element of this vector space. Okay, so identity exists. Okay, so identity satisfied, identity property satisfied, right? Now the remaining condition is inverse. Okay, so let's check it. Okay, wait, see, here I have made a little mistake. Okay, see how it was defined, 1 0 plus 0 1 is equal to this plus last one. Okay, so this plus this 2. Okay, and there was 0 plus 0, b plus c, right? So it will be 0, right? So make it correct, right? And again you can see that this and this is not equal, so commutativity fails, right? Not a big issue, but you can make a correction here, right, for a better notes, right? Now what is the remaining condition? The remaining condition is last one, right? So check the inverse. What about inverse? Inverse. So see, what is the property of an inverse? That is, suppose you have an element, right, and you are adding it with another element, right, and as a result you are getting the identity element, right? What is identity? 1 and 1. Okay, so we have a, this is our vector, right? Now choose such kind of vector such that when you operate it in this property, so that you will get the identity elements here, right? So see, if here is a b, right, so you can choose here 1 by a and 1 by b, right? Why? Because these are from real numbers, right? So see, if you choose a b, right, and you choose another vector, this one, right, so when you multiply it, it will be 1, this into this, it will be equal to 1, this into this, it will be equal to 1. What does it mean? That inverse also exists, right? But there is a catch. That's why I am saying that this question is very beautiful, right? See, you will get inverse for each and every element, right, of this form, but there is only one element for which there will be no inverse, right? So suppose if a is my 0, right, a equal to 0 and b equal to 0, choose it. This is a counter example, right? See, if you choose a equal to 0 and b equal to 0, right, so right here it will be 0 and it will be 0, plus choose any element, right, so that when you operate you will get this one, right? So if you choose anything, choose any element, right? So if you choosing here c and d, right, this is your 0 vector, right, and this is your another vector, right, which you are supposing to be inverse, right? So when you choose like that and when you operate addition, what will you get? You will get this into this according to the given condition of usual addition, right? This into this, what it will be? It will be equal to 0. This into this, a into c means 0, right? Similarly, this into this will be equal to 0, right? Whatever you choose here, right, the result will always be 0 0, right, which is not an identity element. Why? Because in this case the identity element is 1 1, right, and you will never get this identity element for this 0, right? What does it mean? That the inverse of this element does not exist, right? So write inverse of the element 0 0 does not exist, right? and the inverse for rest of other elements will exist, but for this one does not exist, right? So the inverse property fails. Inverse fails, right? That's why this is not a vector space, right? This was a beautiful question. Okay, so next, I hope I am able to make you clear each and everything, right? So next, see what it is saying. Oh, so basically this is a descriptive type question. Okay, we have to prove that this one, right? So let's read the question. What it is saying? It is saying that a real valued function f defined on the real line is called an even function if this holds for each real number t, right? Basically here they are saying that if a function satisfies this condition, right, that f of minus t equal to f of t, then that function will be called even function, right? So this is our given data, right? So what is the question? The question is that prove that the set of even functions defined on the real line with the operations of addition and scalar multiplication defined by this and this is a vector space. So basically we have to prove that the set of all even functions of real line forms a vector space, right? So for that, at first we have to construct the set V, right? So let's do it. V equal to, how it will look like? See, set of even functions, right, defined on the real line. What does it mean? That there is a function, right, defined from R to R, right, such that what kind of function? This is even function, right? And what is even function? If that satisfies this condition. What does it mean? Such that f is my even, right, means this one equal to f of t, right, where t belongs to R for each real number t, right? So this is my V. Okay, now what we have to prove? We have to prove the remaining conditions, right? And here one more thing is given, that the addition is defined like that and the scalar multiplication is defined like that. So write it. So what is given? F plus g of s equal to f of s, right, plus g of s, and cf of s is equal to c into f of s, right? This is my given data. Now by using this one we have to prove that this set forms a vector space, right? So what was the definition of our vector space? That is, let V is a set, right, it is closed under addition and scalar multiplication, right? After that it satisfies commutativity, associativity, identity and inverse under addition, and the remaining 4 conditions under scalar multiplication, right? Only then we say that this V is a vector space, right? So at first let's prove this one, that closure under addition, right? See, closure under addition. Okay, so for that what we have to take? At first we will let two elements from the set V, right? So let f and g belongs to V, right? Since f and g belongs to V, what does it mean? It implies that f and g are my even functions, means f of t will be equal to f of minus t, right? And g of t, it will also be equal to g of minus t, right? So now we have to prove that f plus g also belongs to V. So let's do it. F plus g over t. Okay, now break it. What it will be? It will be equal to f of t plus g of t. Okay, which is equal to c. What is f of t? F of t is equal to f of minus t. So write it, f of minus t plus g of t is equal to g of minus t, right, from the given condition we have, right? So this is equal to, this is minus t. Okay, sorry for, this is actually minus t, right? G of minus t. Okay, and this is also g of minus t and f of minus t, right? so don't be confused about that. Now f of minus t and g of minus t, what does it mean? It means that f plus g of minus t, right, by using the properties of function, right? So see what we get. We get that f plus g of t is equal to f plus g of minus t, right? Means f plus g is an even function, right? Since this is an even function, it implies that f plus g also belongs to v, right? So closure under addition satisfies. Okay, now we will go for scalar multiplication. Okay, so this one is satisfied. Now this one, closure under scalar multiplication. Okay, see, so for that we have to let two elements, one from field and one from v. So let f belongs to v and c belongs to field. What is my field? Field is my real number. Okay, now see, okay, since f belongs to v, it implies that f of t is equal to f of minus t, right? Now see, c of f of t, what it will be? It will be equal to, see, what is f of t? F of t is equal to f of minus t. So c into, instead of f of t, we will write f of minus t, right, which is equal to cf into minus of t, right? So what we get? We get that c of ft is equal to c of f of minus t, right? What does it mean? That this is an even function, so this one also belongs, means c of f of t also belongs to v. What does it mean? That the set v is closed under scalar multiplication too, right? So the second condition is also satisfied. Right, now we will prove these four conditions under addition, right? So see, under addition I am going to prove commutativity, right? So do it. Let f and g belongs to v. It implies that f of t will be equal to f of minus t, and similarly g of t will be equal to g of minus t by using the property of, by using the condition of the v, right? Now see, what is f plus g? F plus g, right, of t, what it will be? It will be equal to f of t plus g of t, right? Now do it. G plus f of t, what it will be? It will be equal to g of t plus f of t, right? And since this is from real number, this is from real number, right, and this is from real number, this is from real number, and we know that commutativity in real numbers is allowed, right? So we can take it like f of t plus g of t, right? So this one is equal to this one, right? So what does it mean? That commutativity will also satisfy, right? So now next, associativity, right? So how can we prove the associativity? We know that function satisfies the associative property, right? So it will satisfy the associativity. You can check, right? No issue. So now we will check for identity, right? So see, identity. Okay, so what will be the identity element, right? So see, we know about the zero vector, right? 0 of x. Okay, does it belongs to v? There is a question, does it belongs to v or not? Okay, so let's prove it. We know that 0 of x equal to 0 and 0 of minus x will also be equal to 0, right? What does it imply? It implies that 0 of x is equal to 0 of minus x, right? Means this 0 of x will belongs to v, right? And we can say that this is the identity element. Why? Take any element f of t from v, okay, and you can operate it with 0 vector plus 0 of t, okay? It will be equal to f of t plus 0 of t equal to 0, right, will be equal to f of t, right? So we are choosing a vector, right, and we are operating it with the 0 vector, and we are getting the same vector as a result, right. That's why 0 vector is the identity element. Okay, so now we will talk about the inverse, right. So let f of t belongs to v, right. What does it imply? It will imply that f of t will be equal to f of minus t, right. Now see, now we will check that does minus of f of t belongs to v or not, right. Now let's check it, that is it belongs or not. See, minus of f of minus t, it will be equal to minus of f of minus t, okay, and it is equal to, see, what is f of minus t? It will be equal to f of t, right. So it will be f of t, right, which is equal to minus of f of t, right. So what we get that this one is equal to this one, right. So see what we get that minus of f of t is equal to minus of f of minus of t, right. So see, what is this? It means that minus f is even function, right. So it implies that minus of f belongs to v, right. So now operate it with any f. If there is f and you are operating with minus f, what it will be? It will be always equal to 0 vector, right, which is my identity. Means for each f there exists a minus f, right, which is my inverse. Means inverse exists, right. So under addition all the 4 properties satisfied, right. Now we will check for scalar multiplication, right. So let's move it. Scalar multiplication, okay. What was the first condition? First condition was 1 into v equal to v, right. So this is obvious. If you choose any even function and you are multiplying with 1, you will get that one only, right. So this condition satisfies. What was the second condition? The second condition was ab into x equal to a into b of a into bx, right. This was my condition. So let's do it. If you choose ab of f will be equal to a of, and if you do it you will get this result, right. No need to check that much right now, but you have to do. Why? Because you are the learner, right. When you do more questions you will think more and it will enhance your basics, okay. So this is your homework. So now what is the third one? Third one was a into x plus y, it will be equal to ax plus ay, right. So you can check it also, right. You choose a and f plus g, right. And you can see that by the properties of functions you will get all the results, right, a and g. And what was the fourth one? It was a plus b, right, into f, right. So you will get this one. You can try it, okay. This will all satisfy. So this will be also your homework, right. I am not going to prove all of these things, right. So see what we have done. We have taken a set v. Under addition it is closed, under scalar multiplication it is closed, under addition it satisfies commutativity, associativity, identity and inverse, right. And under scalar multiplication it will also satisfy the remaining 4 conditions, right. That's why this set is a vector space, right. What was the set? The set was this one, set of all even function, right. So v is a vector space, we have proved. So this question has been done. So next, what it is saying, see which of the following is or are vector spaces, right. So let's check it. What is option A? Option A is v equal to px equal to this one. See what is this? This is set of all real polynomials degree up to n, right. And we have already proved that this forms a vector space, right. So yes, option A forms a vector space, right. So this is my correct, right? What about the second one? B equal to this one over R, right? So we will check it. Okay, what is C? B equal to this one. See, this is the set of all real matrices of order m cross n, right? So it will also form a vector space. We already proved it, right? Similarly, set of all real valued function, this will also form a vector space, right? Now what about this one? See, what it is saying, that v equal to a function from 0 to 1 to R and has a local maxima at x equal to 1/2. Here is a new term, local maxima. What is local maxima? See, what is maxima? Or see, at which point, suppose this is a function, right? Now at which point this function attains its maximum value? F of x attains maximum value, right? That point is called maximum or local maxima point. Okay, that is called maxima point. Okay, you will read it in real analysis in a very detail. Okay, so wait for that lecture, I will make on that also, right? So I think you get the clear idea that what is maxima, at which point the function attains its maximum value, right? So what kind of functions are there in V? A function which is defined on this interval, right, and which local maxima is 1/2, right? So see, so are you able to think such a functions? So yeah, f of x, it will be equal to minus x minus 1/2 whole square, right? See, what is the maximum of it? It is x equal to 1/2, right? At x equal to 1/2, this function attains its maximum value, right? You can check, when you put 1/2, the value of fx will be 0, right? When you put any other value, it will be less than 0, right? If you take any other value other than 1/2, it will be less than 0, right? Which is negative, and we know that 0 is greater than all the negative numbers, right? So fx attains its maxima at 0, right? Till now it is clear. Now see, does the additive inverse of fx exist? See, what is additive inverse? If you check f of minus of f of x, what it will be? It will be, this will be plus x minus 1/2, right? So we are getting this function as minus of fx, right? Now see, what is the maximum value of it? Is it 1/2 or anything else? If you put 1/2, it will be 0, right? If you put x equal to 1, right? If you put x equal to 1, then what will be the value of the function? The function value will be 1 minus 1/2 square is equal to 1/2 square is equal to 1/4, right? And we know that 1/4 is greater than 0. What does it mean? It means that x equal to 1/2 is not maxima of minus of f of x, right? Which implies that minus of f of x does not belongs to V, right? Now see, since additive inverse of this function does not exist in V, that's why we can say that the set V will not form a vector space, right? So this is not a vector space, and this is your counter example, right? So you can think many and more functions, okay, but one is enough, right? So next, see what it is saying. It is saying that let U and W be vector spaces over a field K, right? Let V be the set of ordered pairs UV, where U belongs to capital U and W belongs to capital W, right? So that V is a vector space over K with addition in V and scalar multiplication on V defined by this one, right? So see, what is this? I will discuss it later, okay? So at first, right, what is given? See, given that what is given, that U over K is a vector space, right? U is a vector space over the field K, and this is my notation, right? And W over K is a vector space, right? Is vector space, right? Oh, sorry, it will be better to write R instead of is. Okay, so okay, I am writing UK and WK are vector spaces. Okay, now they are defining a set V, right? So my V is equal to, how is it defined? V be the set of ordered pairs UV, right? So V is the set of ordered pair U and W, sorry, not V, W. Okay, such that where U is from vector space U and W is from vector space W. Okay, so this is the set V. Okay, now how are the operations defined? This one, right? That addition is defined as UW plus U dash W dash is equal to U plus U dash W plus W dash, right? And scalar multiplication is defined as UW is equal to KU KW, right? Now we have to prove that this set forms a vector space, okay, over K, right, over the same field. Okay, now see what is this. This is basically component wise addition, right? And this is component wise scalar multiplication, and we have proved it, right? For what? For A, B, C, D. Okay, so you can prove further, right? It will be easy for you, and I think that you will be able to do it, right, without any problem. So it will be your homework. What will you do? So you are constructing a set. Now prove that it is closed under addition and scalar multiplication, then prove all the properties and all the properties, right? So this is your homework. If you find any difficulty, then comment section is only for you, right? I will make you reply. See, here is a term called external direct product. This space B is called external direct product. Why? See, direct product, right? Then internal direct product, external direct product, right? We will discuss these terms later, right? So why it is called external? Why? Because the elements are coming from two different vector spaces, right? U and V, this is a tuple, right? And the elements are coming from two different vector spaces. That's why it is called external direct product. Okay, and when the elements will come from single vector space, then we will call this set a internal direct product, right? And we will discuss this thing in further lectures, don't worry, right? So just focus to prove this one, right? So next, now see what it is saying. It is saying that which of the following is not a vector space, right? So we have to check. What are the options? C2 over R, C2 over Z, R2 over C, R2 over R, right? So what is C? Basically C is the set of complex number, right? And what is C2? And C2 is the set of two tuples, right? C2 is the set of two tuples, right, where the entries are from set of complex numbers, right? Now we have to check that whether they are forming a vector space or not. So we will go from the basic, right? What was the condition? Means what was the definition? The definition was that a vector space, the definition was that a set is called a vector space over a field F, right? It means that a vector space is defined on a field, right? So what is the conclusion? The conclusion is that a vector space is always defined on a field, right? So now we will check that whether these are fields or not, right? So let's check. So recently I have given you the idea of field, right? I have given something about field, that yes, this belongs to field, this is the property of field, but I have not given you the full definition of field, right? So now I am going to introduce with the definition of the field, right? So see, what is a field? You can remember it, this is very easy. See, I have written it for you. So suppose there is a set, right? I am giving the name F, okay? Suppose there is a set F, right? So then this set is called a field if it satisfies these conditions. What conditions? If F is closed under addition and multiplication, right? This is step 1. F is closed under addition and multiplication, right? And see, here it is only multiplication, not scalar multiplication, right? So here it is normal multiplication. So what is it? A set is called a field if it satisfies closure property under addition and closure property under multiplication. After that, it will satisfy these conditions under addition and this condition under multiplication also, okay? And plus it will satisfy one more condition, distributive law, right? So when a set satisfies all of these conditions, then we will call it as a field, right? And see, here multiplicative inverse will exist only for non-zero elements, right? And see, what is E? So remember, E represents identity, right? This is standard notation, okay? E means identity element, right? So now we will check here. So see, what about Z? Do you think that Z will form a field? No. Why? Because if you take 2, right, and you think that what is the inverse of 2, right? So it is 1/2 equal to 1. And what is 1? It is the multiplicative identity, right? So 1/2 is the inverse of 2, right? But see, 1/2 does not belongs to the set Z, right? What does it mean? It means that multiplicative inverse does not exist for Z, right? That's why this condition fails. That's why Z is not a field, right? Since this is not a field, it means that you can't define a vector space over it, right? The first condition is failed. That's why this option is also discarded, right? Sorry, it will be here. This is not a vector space, right? Since this is not a vector space and the question is asking that which is not a vector space, yes, this is not a vector space, right? And what about this one? This is the set of all 2 tuples, right, where entries are from R. What does it mean? Basically it means that this is AB, right, and A and B are from real numbers. And we have seen many examples that under usual addition and under usual scalar multiplication, right, means component wise addition and component wise multiplication, it will form a vector space, right? So you have to check it. This is your homework, right? Prove that R2/R is a vector space. Similarly, this will also form a vector space. Here the entries will be from complex number, right? This is also your homework. Do it yourself. And if you find any difficulty in it, then comment section is only for you. Comment your doubts, comment your questions, right? I will make a proper reply to you. Okay. Now what about this one? R2/C. So see. Okay, at first let me write it like that. R2/C. Okay. So see, there was a condition that there was a condition what, that V/F, right? So V is a vector space. Only what was the first step? That it should be closed under addition and scalar multiplication, right? So we will check this one, right? So what was it? That Cx, it should belongs to V, right? This is the scalar multiplication where C is from the field and X is from V, and their multiplication should belongs to V, right? So like that here, if we compare, then we will get that this is my V and this is my F, right? So now we will check this condition R2. So how does the elements from R2 will look like? The elements from R2 will looks like this one, that AB, right? This is my X, right? AB belongs to my R2, right? Now we are choosing an element from field, right? We will choose an element from field, right? Here field is my C, so we are choosing, and we know that iota is a member of complex number, right? Because iota is a complex number, so we are multiplying it with a scalar with an element of field I. Okay, so what will you get? You will get IA and IB. And see, this is a complex number, this is a complex number, right? And this does not belongs to V. Why? Means this does not belongs to R2. Why? Because R2 is the set of all two tuples from entries from real numbers, right? And we are getting entries from complex number. It means that this one does not belongs to R2, right? So closure under scalar multiplication fails, right? Closure under scalar multiplication fails. That's why this is not a vector space. Okay, this will not be a vector space. And according to the question, they are asking that which of the following is not a vector space. So yes, B was correct, C is also correct. Since this will form a vector space and this will form a vector space, so according to the question, this is my wrong answer, right? So see, there are many questions about it. I am going to give you some of them, right? See now, if I ask you that R over R2, right, does it form a vector space? Then C over C2, will it form a vector space? Just think about that. The question is no, it will not form a vector space. Why? Because R2 and C2, these are not fields. Yes, R and C, these two will form a field, but R2 and C2 is not a field, right? Now I want a counter example from you, that among them which property does not satisfy, right? This is your homework. I want the answer in comment section, right? So find which one does not satisfy for this case, right? And there is one trick also. What is that? To verify. See, suppose you have given that R over R, right? Then you have given that R over C, then C over R, right? And C over C. Now if I ask that which of them forms a vector space, right? So always remember, a vector space, a set forms a vector space if it is a set, right? Then it will forms a vector space over its subset only, right? It will form a vector space, but a subset will not form a vector space over set, right? This will not form a vector space, right? I will discuss this thing later, but I am giving you a little bit hint that what we will do it in future, right? With this concept, you will get a lot of questions from many competitive exams like JAM, NET, CUT, etc. Okay. So see, this is R, this is R, and we know that every set is a subset of itself. Yes. So this is set, this is subset. So yes, this will form a vector space, right? Similarly, this is set and this is superset, not subset, right? Set, subset, this is not a vector space, right? Similarly, this is my set, this is my subset. Yes, this will form a vector space, right? And here also, this is my set and this is my subset. Yes, this will also form a vector space, right? So if you apply this condition here, so see, here was R2 over C, right? So see, no, I am not talking about this thing, right? Leave it. But just remember this thing, right? We will discuss these things in further lectures when I will make videos for CSIR, NET, CSIR, GATE, right? Then I will teach you many shortcut tricks also. Okay, but now make your basics very strong, right? So next, now what it is saying? It is saying that let V be the set of ordered pairs AB of real numbers with addition in V and scalar multiplication on V defined by this one, right? And this one, so that V satisfies all the axioms of a vector space except this one. Oh, this is very easy. I think we have done the similar questions before, right? So do it yourself, right? So finally we have covered all the 20 questions related to vector space only. Okay, here I have, so see, here I have not included any single questions of any other topic like subspaces or any other thing, right? Because I am going to make a separate video for subspaces. There I will discuss a lot of questions, right? So this lecture is especially designed for vector space only. I hope I am able to make you each and everything very clear, right? So finally, summary, right? So what was the summary of this lecture? So see what we have discussed. At first we have seen the introduction, after that we have seen the applications, then we have seen the definition of vector space, right? And then we have seen a theorem, then set of then we have seen that the set of convergent sequences, set of integrable differentiable functions, set of polynomials degree up to n, set of matrices, these forms a vector space. Okay, and further we have done some theorems and results, right? And then what we have done, we have covered all the questions from standard books from the standard book on vector spaces only, right? As I have said that in this lecture there are questions only for vector spaces. I have not included about subspace, right? This is the next topic of our lecture. Okay, and then we have seen some of them, that how to approach standard questions from very basic, right? This will help you to solve the question of NET and GATE, right? So I am building your basic, right, so that you will be able to crack this kind of examination, right? So what is the references of this lecture, means which books I have used here. So see, I have used 3 standard books, right? This is considered to be the very basic book for the beginners, right? And this is the advanced book for the learners, right? And this is a very special book, right? Especially if you are preparing for IIT JAM, right? If you are preparing for GATE or CSIR NET, right? Then this book is an ideal book, right? And I believe that this is the best book in the market for these 3 exams, right? So finally, thank you for watching and all the best for your mathematical journey. And I have written a very beautiful lines for you by Stephen Banach. He was a great mathematician. You will read a lot of works from him in future, right, when you study more. So mathematics is the most beautiful and most powerful creation of human spirit, right? So with this line I want to end this lecture. So all the best for your further journey.